Business statistics is one of the most critical and most vital modules when it comes to data analytics, data science, or even AI. Nowadays, many people are moving towards generative AI because there is a wave of generative AI. Many companies are investing a lot into generative AI. Number of jobs in the generative AI field is also increasing drastically, and hence many people they are expecting to become generative AI engineers very soon. Now, just to let you know, the generative AI career path was already shared in one of my previous videos. In case you have not watched it, please go ahead and watch it out. So, this video is all about business statistics, and business statistics, to be very honest, is one of the most important modules even before you jump into machine learning, deep learning, or any other topics, because everything is related to statistics. Data cleaning. If you don't understand measures of central tendency, you don't understand mean, median, mode, you will not be able to impute missing values. If you don't understand standardization and normalization concepts, you will not be able to perform feature scaling. If you don't understand hypothesis testing, you will not be able to do a lot of things when it comes to descriptive and inferential statistics. So many such topics are prerequisite for machine learning, NLP, and various other topics. Hence, statistics is very important. People usually go for bachelor's degree and master's degree. We can understand how important statistics is because it is the core concept. And in this video, I'm going to give you all the necessary information that you need to study before taking your next step. So this video is going to be the final video, like this is going to be the end-to-end video for you. Apart from this video, you do not need any other topics. Going forward, while you learn machine learning and various other things, multiple things you will be learning on the go. So this video is going to be an end-to-end business statistics video that you need. Apart from this, you might also need some knowledge on mathematics, like eigenvalues, eigenvectors, and various other topics related to mathematics. In case you want me to come up with a mathematics related dedicated video, just let me know in the comment section, write down mathematics, and I will come up with a video very soon. Just to let you know that the reason behind coming up with this end-to-end statistics video is one of my previous videos, which was on EDA, that was like 5 hours long video, and we got more than 100k views on that video. And because of that kind of love and support from you guys, it was very overwhelming for me, and because of which I am here with this end-to-end statistics video where everything will be covered. There will be topics like descriptive statistics, inferential statistics, probability distribution, hypothesis testing, covariance, correlation. Multiple topics are going to be covered. You can check out the list of all the topics in the description as part of chapters. If you want to navigate to a future chapter, just click on the timestamp and you will be able to navigate. So this is all you need. Apart from that, there are many other videos coming up on my channel very soon. In case you want to support my channel, what I need from you is like, share, and subscribe the channel. And do not forget to comment down, because comments are very important, because that's how YouTube works, right? This is not an entertainment channel, this is an educational channel, and getting growth in an educational channel is very difficult. You can see I have 85,000 subscribers, but on an average I get like 1,000 2,000 views per video, which is very difficult for me to grow. So from you guys, what I need is comments. Anything and everything that you need from me, just comment down. Apart from that, please enjoy this video, go through this video in depth. In case you find there is a code problem or there is an understanding problem, in case you have any doubts in this entire 6 hours video, let me know in the comment section, and I am keeping an eye on the comment section very actively. That's it. My name is Satyajit Pattnaik, and I welcome you to this video. See you in the video. Hi, welcome to this module on statistics. In this video, we shall be talking about the introduction to statistics. What exactly is statistics, and how statistics plays a vital role in the field of data analytics and data science? Basically, the statistical analysis is meant to collect and study information available in large quantities. Statistics is simply a branch of mathematics where computation is done over a bulk of data using charts, tables, graphs, etc. For example, you want to analyze two numerical columns. Let's say you have data. There are multiple columns in it. There could be name, gender, tenure, age, salary, so many things. Imagine you are analyzing two numerical attributes. Numerical attributes are those attributes those have data in format of numbers. For example, age. Let's say age of 10 customers that you have are something like this. Let's say we'll consider four examples. Similarly, we also have salary. Let's say the salary at age 25 is this, age 29 is around this, 31 is around this, and 35 is around this. And you start analyzing using some charts. There is a chart called as scatter plot. For example, age goes into the x-axis and salary goes into the y-axis. So let's try to plot each one of them roughly. Let's say we have 5, 10, 15, 20, 25, 30, 35. Around 25, we have 5,000, 10,000, 15,000, 20,000. Now, if I plot this age 25 and 10,000 salary, which is somewhere around here. Age 29 and 12,000 is somewhere around here. Age 31 and 16,000 is somewhere around here. Age 35 and 20,000 is somewhere around here. If I start plotting the graph, this is how the graph looks like, which clearly indicates that there is an increasing trend. That means if age increases, your salary increases as well. This is what the data is telling us using this particular chart. So statistics, as I told you, is nothing but a branch of mathematics where computation is done over a bulk of data using charts, tables, and graphs. The data collected for analysis here is called measurements. Now, if we have to measure the data based on a scenario, a sample is taken out of a population. Population is simply nothing but, imagine if I ask you to find the average age of people in Japan or Indonesia or Malaysia, wherever you are coming from. Let's say, how do you find the average age of people in Japan or in Hong Kong or in China? Now, definitely you are not going to ask each and every one of that country, right? For an example, we'll take an example. I'm not pretty sure about the population of Japan, but imagine the population of Japan is around 40 million. Imagine. Okay. Now, I'm not going to ask each one of them. Now, asking each one of them is going to be, this entire thing is called as population. The entire 40 million. And taking feedbacks, taking outputs, taking statistics from a population is completely a different scenario, and it is not feasible. Usually what we do is we kind of do some sampling out of it. What if I go to different location, I talk to different kind of people, and I take a small chunk, maybe 1,000 or 2,000 people, and then I ask each one of them what is their age, and then take an average out of it, and just imagine the average age is 39. Now this is the average age of sample, not of the population, right? So this is the difference between population and sample. Definitely there are many and many sampling techniques that we will be covering in the future. based on which you can understand how samples are created in different scenarios. But for the time being, I hope you understand the difference between population and sample. Then analysis or calculation is done for the following measurement. I hope you got an initial idea about statistics. Statistics is very vital for data analytics, and we are going to learn a lots and lots of concepts related to statistics in our future videos. That's it for this particular video. See you in the next video. Bye. Hi, welcome back to this module on statistics. In this video, we shall be talking about types of data and statistical analysis. This is how the agenda looks like. We'll get started with the types of statistics, which is descriptive and inferential. Then we'll get started with each one of them. What exactly is descriptive? What exactly is inferential statistics? And lastly, we'll also be talking about the different types of data, which is majorly categorical and numerical, otherwise known as qualitative and quantitative data. See you in the next video. Hi, welcome back to this module on statistics. In this video, we shall be focusing on descriptive statistics. In the previous video, we learned that statistics is majorly of two types, which is descriptive and inferential. But what exactly is descriptive statistics? Descriptive statistics, as the name says, that means describing. That means descriptive statistics summarizes or describes the characteristics of a data. Imagine you have a data set, and that could be a customer related data. Let's say you have 1,000 customers information here. You have age, salary, gender, etc., etc. So many features. The what part is basically nothing but the descriptive statistics. That means what is the data telling you? What is the average age? What is the total population? What population are males? What population are female? What is the average salary? All this information are nothing but a part of your descriptive statistics. That means the describing the characteristics of a data set. Descriptive statistics consists of three basic categories of measurements: measures of central tendency, measures of variability or spread, and frequency distribution. Measures of central tendency describe the center of the data set, which is mean, median, and mode. What do you mean by each one of them? In short, let me explain you each one of them using some examples. Let's say I have 5 people, and the age of these 5 people are 25, 30, 15, 25, 35. Now, what if I ask you what is the average age? We already know what is average. Average is nothing but the sum of all these numbers divided by the total population. This is nothing but the symbol for summation. Now, what is that? This is nothing but 25 plus 30 plus 15 plus 25 plus 35 divided by 5, which is 55, 15, 70, 50, 120, 130 divided by 5, and this becomes 26. So the average age becomes 26. Let me confirm it using a calculator. 25 plus 30 plus 15 plus 25 plus 35 is 130 divided by 5 is 26. Now this is the average. The mean is nothing but the average. Mean is nothing but the statistical name of average. So here the mean is called 26. Mean is also denoted by the symbol mu. What will be median? Median is simply nothing but the middle value. In order to find the middle value, the first thing that you need to do is to sort these values. Let's say if I start writing these numbers from smallest to the largest numbers, first one will be 15, then comes 25, 25, 30 and 35. And the middle value is 25. So this becomes your median. What if you have 6 numbers? Let's say you also have 40. Now you have 6 numbers. 25 cannot be the middle value. The middle value is now 25 and 30 both. So here the median will be the average of these two numbers, which will be 27.5. Mode is something that is usually applicable for categorical data. But in this particular example, the mode will also be 25. Why? Because it has the maximum number of occurrences. Mode is mostly used for categorical data. For example, you have gender. You have 10 customers and or else 5 customers. One of them is male, one of them is female, one of them is empty, one of them is female, one of them is female. Now what if you have data like this? Out of these 5 records, one of these records have a missing value. That means you have to deal with it. Now you can deal it using mode. Here the mode will be female. Why? Female has 3 occurrences, male has 1. So normally mode is nothing but that particular attribute which has the largest amount of occurrences, which has the maximum amount of occurrences. What if you have 2 females and 2 males? In that case, your mode could be both of them. This scenario is called as bimodal. Bimodal. Okay. So anyways, we will be covering measures of central tendency in depth in one of our future videos. Next is going to be measures of variability. Describes the dispersion of the data set, which is variance and standard deviation. Now, what exactly is standard deviation and what is variance? Definitely, we will be understanding in depth in some of our future videos using mathematical examples as well. In simple terms, if you want to remember what is standard deviation, the formula of standard deviation, which is symbolized as sigma, is nothing but summation. Again, summation is nothing but addition. Summation of xi minus mu square divided by n root over. Now, trust me, do not get panicked using this formula. Do not get panic attack by seeing this formula. This formula will be explained in depth in some of our future videos. The internal part of it without the square root part is nothing but your variance. Okay. Again, theoretically and practically, we will have separate classes for that. And the next part is measures of frequency distribution describe the occurrence of data within the data set, which is called as count. Now, this is a high level idea about descriptive statistics. We have in-depth classes on each of these topics in the future. That's all about this particular video on descriptive statistics. In the next video, we shall be explaining you what is inferential statistics, and then we'll jump into these respective videos. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about inferential statistics. In the previous videos, we understood what exactly is statistics, what are the different types of statistics, which is descriptive and inferential. We somehow got a basic understanding on descriptive part, However, we still have to go through multiple videos on the subtopics of descriptive statistics. But what exactly is inferential statistics? In simple terms, inferential statistics is nothing but a branch of statistics that makes the use of various analytical tools to draw inferences about the population data from the sample data. The two main areas of inferential statistics is estimating parameter and hypothesis testing. Well, a set of method that is used to draw a conclusion about the characteristics of population based on the sample of the data. As we discussed one of the examples, what if I want you to get the average age of an entire country? Let it be Japan, Korea, or any of these countries. Let's say country X. Is it possible to ask each one of them about the age? No, it's not possible. So what we usually do is we infer the same from a sample out of it. For example, we talk to 100 people from different locations of that country, different age groups, different types of people, and then try to understand what each of their ages are. And then we find out, oh, the average age is probably 40. So this average age is definitely not from the population, but from the sample data. So in short, we are inferring that the population, the average age of country X could be 40. That is what we are inferring. And that is all about inferential statistics. A set of method that is used to draw a conclusion about the characteristics of population based on the sample of the data. Used to find the population parameter when you have no initial number to start with. We will be covering these topics in depth. That's all about the basics of inferential statistics. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about the different types of data. One of the most basic concepts to understand before getting into the future topics. We already know the importance of data. We already know that data is vital for solving a data analytics or a data science problem. But what exactly is data? Data is majorly of two types. One is going to be categorical data and one is going to be numerical data. Categorical data, some of the examples could be, imagine you are analyzing some data. It could be an Excel sheet or something like that. Multiple columns are there. One of these columns are gender. Now gender has values like male, female, and so on. Now this is an example of categorical data because they are in categories. Another example will be location. Let's say multiple customers' location are captured in the data. Somebody stays in Japan, some stays in Korea, some stays in Indonesia, some in Malaysia. So those kind of data are also called as categorical data. Let's say you start analyzing a column which is age, which is having values like 25, 29. It basically has your age of multiple customers or your or multiple people. Now these kind of columns are your numerical columns. Now talking about the statistical terminology, we usually term categorical features or categorical variables as qualitative data. Similarly, numericals are termed as quantitative data. Let's try to get into qualitative data. What exactly is qualitative data and what are the further subcategories under it? So qualitative data or categorical data. Qualitative data, also known as categorical data, describes the data that fits into categories. Qualitative data are not numerical, of course. Categorical information involves categorical variables that describe the features such as a person's gender, hometown, etc. Gender could be male, female, hometown could be any country, Indonesia, Malaysia, Japan, whatever it is. These are all your categorical or qualitative data. Sometimes categorical data can hold numerical values as well, but those values do not have a mathematical sense. For example, examples of the categorical data are birth date. Now, what if somebody's birth date is something like this? Now, these are combination of numerical values. These are all your numbers, but it is termed as a categorical data, not as a numerical data. We also have favorite sport, school postcode. Here, the birth date and school postcode hold the quantitative values like this. They have numbers in it, but they don't give any numerical meaning. There is no numerical meaning to it. So, these kind of data are considered as qualitative data, even though they have quantitative values, right? So, inside qualitative data, majorly there are two types of data. So, data, as I told you, data is of two types, your qualitative and your quantitative. Inside qualitative comes your nominal and ordinal data. Nominal data is one of the types of qualitative information which helps to label the variables without providing the numerical value. Nominal data is also called the nominal scale. It cannot be ordered and measured. This is the most important feature of nominal data, that it cannot be ordered. But sometimes the data can be qualitative and quantitative. Examples of nominal data are letters, symbols, words, gender. Now, for example, we consider gender, male and female. We cannot order it. We cannot say males are superior than females or vice versa. So there is no ordering. Okay. So the nominal data are examined using the grouping method. In this method, the data are grouped into categories, and then the frequency or the percentage of the data can be calculated. These data are visually represented using pie charts. For example, you start analyzing gender. A better chart will be a pie chart, something like this. Let's say female and male, let's say 45% and 65%. Sorry, 45% and 55%. My bad, 55%. They could also be represented in a bar chart, male, female, and male. So, something like that, right? Now, of course, in this example, male are 55%, so they should look like this. But I'm just giving examples, right? That they can be represented visually using pie charts, using bar charts, and so on. Now, moving towards the ordinal data. Of course, as the name suggests, ordinal has something to do with orders or ordering. The significant feature of ordinal data is that they can be ordered. The first and foremost feature of ordinal data. Ordinal data, sometimes categorical data, can hold numerical values as we already discussed, but those values do not have a mathematical sense, right? We already discussed this. Ordinal data are some of these variables which are used mostly in surveys, finance, economics, questionnaires, and so on. What are some of the examples of ordinal data? One example is economic status. Economic status could be high, it could be mid, it could be low, and we already know it's in an order, right? It starts from low to high, right? Or else, let's say you are analyzing students' grading system. Some people have got A, some people have got B, some people have got C, some have got D, and we already know that it's in an order. So these kind of data are called as ordinal data. How do we represent it visually? Ordinal data is commonly represented using a bar chart. These data are investigated and interpreted through many visualization tools. Let's say you start plotting the graphs for economic status, high, low, and medium, right? So these kind of graphs can give you insights that, majority of the people are falling in this category. Low number of people are falling into the low category, like less number of people, right? And so on. So bar chart is going to be a to-go visualization kind of technique to plot and visualize and analyze the ordinal data. The information may be expressed using tables in which each row in the table shows the distinct category. So that's all about your basics of types of data and the qualitative data. We also discussed about nominal and ordinal data. In the next video, we shall be talking about the numerical part, the quantitative part. So see you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about quantitative data. In the last video, we talked about the different types of data in which we discussed about qualitative and quantitative. In this video, we shall be focusing more on the quantitative type of data. What do you mean by quantitative? Simply, quantitative data is also known as numerical data, which represents the numerical value. That is, how much, how often, how many. Numerical data gives information about the quantiles of a specific thing. Some examples of numerical data are height, length, size, weight, and so on. The quantitative data can be classified into two different types of categories. The two major classifications of numerical data are discrete data and continuous data. What exactly is discrete data? Discrete data can take only discrete values. If you have quantitative data, like number of workers in a company, let's say we are talking about a company X. So, for example, you have quantitative data like a number of workers in a company. Could you divide every one of the workers into two parts? It's not possible because the number of workers is discrete data. So, let's try to define discrete data in a better way. Discrete data is a count that involves integers. Only a limited number of values is possible. For example, the number of students in a class. The number of students in a class could be 40, could be 45, could be 50. It cannot be 40.5. It cannot be 39.5. It cannot have these numbers. So discrete data can take only certain values. The data variables cannot be divided into smaller parts. How do we plot discrete data? We can plot using any kind of graphs. It could be a pie chart, or it could be a stem and a leaf plot. It could be anything. Going forward, some other examples of discrete type of data could be, apart from number of students in a class, it could be number of workers in a company, number of languages an individual speaks. For example, I speak 6 different languages. One cannot simply speak 4.5 languages or 3.5 languages. It's not possible. So these type of data are called as discrete data. Now what is continuous data? Continuous data is data that can be calculated. It has an infinite number of probable values that can be selected within a given range. Now, for example, you can measure your height at very precise scales. It could be meters. Let's say my height in meter is 171 meters. In centimeters, it is 171 centimeters. In feet and inches, it is 5 feet 8 inches. So you can measure your height at very precise scales. You can record continuous data at so many different measurements: width, temperature, time, and etc. This is where the key difference with discrete data lies. So This is the example of a continuous data, and I hope everybody is clear with the difference between discrete and continuous data. That's all about this video on quantitative data. In the next video, we shall be talking about several other topics. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about sampling techniques. This is how the agenda looks like for our next few videos. It all starts with population and samples. We'll talk about population and samples. What exactly is population? Population simply is nothing but the entire group that you want to draw conclusions about. And sample is the specific group that you will collect data from. The size of the sample is always less than the total size of a population. For an example, if somebody asks you to find the average age of the entire population of Japan, now it's not possible to talk to each and every person from Japan about their age. Rather, we'll start working on a smaller chunk of data, start capturing data, and then find, oh, the average age is probably around 40. So, this is the difference between population and samples, which we will be covering in depth. Next, we shall be discussing about the types of sampling technique. There are so many types of sampling technique. We will be discussing them. Random sampling, non-probability sampling, population sampling, and so on. We will be, in short, studying about various sampling techniques, population, samples, and all these related topics in the next few videos. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about population and sample. What exactly is population and what is sample? The simplest definition of population is nothing but the entire group that you want to draw conclusions about. The universe of objects that is required to be analyzed is known as population. And sample is nothing but a subset of population. It's a part of population. It is a specific group that you will collect data from. The size of the sample is always less than the total size of population. In research, a population doesn't always refer to people. It can mean a group containing elements of anything you want to study, such as objects, events, organizations, countries, species, organisms, etc. Now, some of the examples of population. What if, as I was giving this example in the last video, what if somebody asks you that what is the average age of a particular country? It could be any country. It could be Japan, Korea, India, Philippines. It could be any country. Imagine a country X. If somebody asks you, can you find the average age of a country? No. It is completely impossible to do it. You cannot simply go and talk to each one of them, ask their age. The moment you probably go from one individual to another individual, already be, a lot of time will be invested in this process. So it is logically not possible to interact with each one of them, get a list of all their ages, and then find their mean value or the average value, right? Instead of that, what you should do is you should divide your country into specific areas. Let's say, what if you divide your countries into four particular sections, or else could be north, could be west, could be east, could be south, and could be central. Or you can divide it as per your own wish. Again, as per your divisions, how about you go and talk to a small chunk of data, probably 10, 15 people from each chunk, and then you take around 100 or 200 samples and then ask what is their average age, and then probably you find it out that the average age is around 40. Now this is what the average age is from the sample data. So that's how the difference between population and sample looks like on paper. In logical sense, in real world scenarios, we never work on population data. Whenever you start working on a data analysis problem, we always starts with a sample data. Once our sample data is created, once we start analyzing it, then we move towards the population data. Like theoretically, it's not possible to work on the entire population, but we usually work on sample data. I hope you understand the concepts between population and sample. In the next videos, we shall be talking about few other topics. Hi, welcome to the module on statistics. In this video, we shall be talking about why sampling is important. We already know what exactly is a sample and what is a population data. So population is nothing but your entire thing. Let's say you are analyzing the people of Japan or people of Korea, which could be in millions. I'm pretty much not sure about the population of Japan. Now, what if you have to analyze them or you want to find something, the average age of a person in Japan? Obviously, you cannot go to each one of them and ask about it, right? So, you always have to work on samples. You always have to work on samples because of this reason. You cannot simply go ahead and talk to the entire population. But what you can do is you can probably got to go and talk to different categories of people in Japan, probably 100 200 people, and then start collecting information and then come to a conclusion that, oh, the average age from this sample is 40, so we can also infer that the average age of the population, entire population in Japan, could be 40. That is the advantage of sampling, right? Gathering data from entire population is not possible. Sampling is applicable in such situation where gathering data from entire population is not possible. Using sampling, one can make information faster. Surveying and measuring everyone is not cost effective. We can easily analyze the data when using the sample of the data. Imagine you have a data worth gigabytes of data. It could be like 100 gigabytes of data. And somebody has asked you to start analyzing and creating some dashboard, some visualization dashboard, or some sort of graphs, right? Now, obviously, if you get started with 100 GB of data, if your computer is not fast enough, probably you might take a lot of time in analyzing the data and then a lot of time in visualizing it because it could be slow, right? So a better approach here will be kind of creating a sample data, probably of some MBs, maybe 500 MB or 200 MB, and then get started with your analysis and your visualization process. Once this is done, and then you can go ahead and change it to the population data. It's possible, right? So it is usually an easier step to analyze a sample data. A smaller set of individuals often results in lesser data collection error. Again, when you are working on small chunk of data, you might have to deal with less data collection issues as compared to population data, right? So these are some of the advantages of why sampling is important. In our next videos, we shall be talking about various other topics. See you in the next video. Bye bye. Hi. In this video, we shall be discussing about the different types of sampling techniques. So far, I hope everybody understood the concepts behind the population and sample. We also know why sampling is important. Now, the next question is, how do we sample? How do we create samples? What are the different sampling techniques? So, sampling techniques are majorly of two types. One is probability and one is non-probability sampling. Probability sampling basically means every member of the population has an equal chance of being selected. Imagine you have an entire population. You want to select some samples out of it. Let's say these are my entire population, and maybe this data, and this data are part of my sample. Now here, selection of a data point from population to the sample is a probabilistic approach. There are further many types of probability sampling. One of them is simple random sampling, stratified sampling, cluster sampling, systematic sampling. What are each one of them? We will be covering in the next videos. But the major concept behind this probability sampling is that they are based on probability. Every member of the population has an equal chance of being selected in the sample data. While talking about non-probability sampling, here samples are selected on basis of judgment or the convenience of accessing data. Now, for example, you have a population, you want to only access the data points, or for example, let's say this is your entire population. Let's say you stay in Japan. Now, you only want to, for example, you stay in Tokyo. What if you only want to access the Tokyo population, and then from that you have to select a smaller subset, and then you are selecting a sample? So here you are selecting based on your convenience. As you stay in Tokyo, it is better for you to talk to people from Tokyo and take views, and that's how you are creating your sample. You are not concerned about other cities in Japan. So that is non-probability sampling. What is the probability of another city's data to be a part of sample? It is completely zero, because the user is giving priority to Tokyo. I hope you are getting my point. So samples are selected on basis of judgment or convenience of accessing data. Largely depends on a research sample selection skills. Some of the non-probability sampling are convenience sampling, purposive sampling, voluntary response sampling, and snowball sampling. We'll be discussing about each one of them in our future videos as well. That's all about this video on the different types of sampling. In the next videos, we shall be jumping into each one of them, and we'll try to understand what each one of them means. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about cluster random sampling. It's again one of the types of probability based sampling technique, cluster random sampling. How do we find samples out of population using this technique? You can see, divide the population into groups, then randomly select the group from all the groups. As you can see in this example, in this pictorial representation, we have a cluster population, and we have 6 clusters: 1, 2, 3, 4, 5, and 6, and we have randomly selected 2 clusters out of it, which is cluster number 3 and cluster number 6. But the most important thing is, how do we form this cluster population? Now there are different steps behind it. Let's try to understand the different steps. The first step is defining your population. And imagine we have a population, but we don't have the clustered population. As in, we don't know which person falls in which cluster. We just have the population data. So we should always start with your population data to which we are intending to study, right? The second step is always dividing your sample into clusters. Now this is the most important part of the process. The quality of your clusters and how well they represent the larger population depends or determines the validity of your results. Ideally, there are some of the criteria that we kind of need to create. Each cluster's population should be as diverse as possible, and there cannot be any repetition. That means if one person is a part of one cluster, that person cannot be a part of any other cluster. So each cluster should have a similar distribution of characteristics as the distribution of the population as a whole. Taken together, the cluster should cover the entire population. Imagine you have entire population 1 million records. Now you are creating clusters out of it. Cluster 1, cluster 2, cluster 3, cluster 4. Let's say cluster 5 and cluster 6. Now each cluster, let's say a person A is a part of cluster, first cluster, he cannot be a part of any other clusters. And each and every cluster, if you combine them, that should make your population. Taken together, the cluster should always cover the entire population. Each cluster should have a similar distribution of characteristics as the distribution of the population. So ideally, each cluster should be a mini representation of the entire population. However, in practice, clusters often do not perfectly represent the population's characteristics, which is quite obvious. Now, if you're analyzing the people from Japan or Korea and you are creating clusters, you cannot guarantee that each cluster will be a replica in terms of characteristics or properties. They could be very similar to the population, but they cannot be a replica. So, in practice, clusters often do not perfectly represent the population's characteristics, which is why this method provides less statistical certainty than the simple random sampling. Because clusters are usually naturally occurring groups, such as schools, cities, households, etc. They are often more homogeneous than the population as a whole. So, after you have done with the step number 2, now comes step number 3, which is randomly selecting clusters to use as your sample. So let's say you already have 6 clusters created. Each cluster is kind of a representation of your population data. It is as diversified as your population data, not a replica, but somehow in the same direction, almost similar. Now we have to randomly select some samples out of it. So let's say we select sample this cluster and this cluster. So cluster 1 and cluster 4. Now these are going to be my sample clusters. So and then we get started with collecting data from these sample clusters and start analyzing them. So that is a pictorial representation of cluster random sampling. I hope you understood the concept behind it. That's all about this particular video. In the next video, we shall be talking about various other sampling techniques. See you in the next video. Bye-bye. Hi, welcome to the module on statistics. In the last video, we discussed about the various types of sampling. We discussed about what exactly is a probability sampling and what is a non-probability sampling. We also kind of talked about the various probability sampling techniques, which is random, systematic, stratified, and cluster. Similarly, we also talked about the various non-probability sampling, which is convenient sampling, purposive, voluntary response, and snowball. This video is dedicatedly going to be on probability sampling. We will be talking about each one of them in this video. So let's get started. Talking about random sampling. Random sampling is simply a type of sampling where you randomly choose a member from population. Imagine this particular example of population. We have person 1, 2, 3, 4 till 12. Now randomly you select 4 records from this particular population. It could be this, this. It could be this. It could be any random samples. It could be any random element from your population. This is simply called as random sampling. Every member and set of member has an equal chance of being selected. Now the probability of getting selected for this person in the sample and the probability of this person to be selected in the sample is same. And that is one of the reasons why it is considered as one of the probabilistic approach, one of the probability sampling technique. Secondly, we will discuss about systematic sampling. Now again you see this population 1 to 12, but here what if you select the every third guy? Imagine the first cursor is on the second person and then you select every third guy. That means 5, 8 and 11. What if you select all the persons who is at the odd location? Maybe 1, 3, 5, 7, 9, 11. So this becomes a sample. This type of systematic sampling is called as, this type of systematic way of selecting samples is called as systematic sampling. This is also called as systematic random sampling. It is very similar to simple random sampling, but in a systematic manner. Put a member of the population in some order and a starting point is chosen as random. The every nth member is selected to be in the sample. After systematic sampling comes stratified sampling. Now, this is one of the most important sampling techniques. Now, what it tells you is that first of all, we have to divide the population into groups. Imagine, I'll give you an example. I have a population of 1000 records. What if I want to create a sample of 100 records? If I talk about simple random, that means randomly I take 100 records. If I talk about systematic random, that means systematically I pick every 10th element, or else from 1 till 1000 I pick every 10th element, 1, then 11, then 21, then 31 and so on. Is this the right way of creating a sample? Probably not. What if in my 1000 records, imagine I have 1000 records and in that let's say I have a combination of male and a female. Let's say male are 600 and female are 400. If you randomly select a sample of 100 records, I cannot guarantee that it will also have the male is to female in the same ratio of 600 is to 400. I cannot guarantee that it will follow the same ratio. I cannot guarantee in simple random sampling. I cannot guarantee in the systematic random sampling as well. So what stratified sampling tells you is that if you have different kinds of population like this, different groups, how about you choose 60 random data points from male and 60 random data points from female and then create your sample data. Now in your sample data, you can see the male is to female ratio is same as the total population data. That means your group distribution is maintained. So the explanation goes like this. First divide the population into groups, then from each group we select members randomly by maintaining the ratio. That is called as stratified sampling. And it is one of the most important type of sampling, right? Because you should always maintain the original distribution, right? After the stratified sampling comes cluster random sampling. What do you mean by cluster random sampling? As the name suggests, we have to create some sort of clusters and then probably from these clusters we have to randomly pick some data points, right? You can see divide the population into groups, then randomly select the group from all the groups. Imagine again I have 1000 customers and let's say you are working on a segmentation problem. You want to segment your customers into different groups. How many groups you don't know. So probably what you do is you use a clustering technique. So clustering technique is one of the advanced techniques which is covered under machine learning. A clustering technique simply means the way you create clusters. For example, if you divide 1000 records into multiple clusters, it could have 3 clusters, it could have 5 clusters. Cluster basically means all the customers, all the people inside this cluster are similar in nature. All the people inside this cluster are similar in nature. All the customers are in this cluster are similar in nature. Similar in nature and similar in nature. And then you randomly pick some records, maybe 600 from here, sorry, not 600, 60 from here, 30 from here, 5 from here, 3 from here, 2 from here, and then becomes your 100 samples. This type of sampling is called as cluster random sampling. So you have to create clusters, and then from the clusters you have to pick samples. That's all about this particular video on probability sampling techniques. I hope you understood each one of them. Practically, we'll try to go through each one of them probably in some of our future videos where we will show you how to create samples and all those things. In this video, that's it. In the next video, we shall be talking about the non-probability sampling techniques. See you. Hi, welcome to this module on statistics. In this video, we shall be talking about the non-probability sampling. Well, in the last video, we discussed about the probability-based sampling. Selection of a sample from a population is based on a probability value. This data point being a part of sample or this data point being a part of sample, the probability remains the same. That kind of sampling is called as probability sampling. In case you are not aware of this concept, please go back to the previous video and get your doubts clarified. In this video, we shall be discussing about the non-probability sampling techniques. The first technique is convenience sampling. What exactly is convenience sampling? A convenience sampling simply includes the individuals who happens to be most accessible to the researcher. Imagine you have your data communities, probably on WhatsApp groups or Telegram groups, and you quickly need to fill up a survey form. What you do is you quickly send your survey links in various WhatsApp groups. That means based on your convenience, you want people to fill the records. That type of sampling is called as convenience sampling. For example, you are researching opinions about student support services in your university. So after each of your classes, you ask your fellow students to complete a survey on the topic. This is a convenient way to gather data. But as you only surveyed students taking the same classes as you are at the same level, the sample is not representative of all the students in your university. That type of sampling is convenience sampling. Next is purposive sampling. Purposive sampling means selecting a sample based on the purpose of the research. Researcher selects the sample by using their expertise and knowledge. Example, you want to know more about the opinions and experiences of disabled students in your university. You have your university and there is a small chunk of people who are having disabilities, some disabled students. So you purposefully select a number of students with different support needs in order to gather a varied range of data on their experiences with student services. So purposely you are selecting this group of people to take some feedbacks. This type of sampling is purposive sampling. The next type is voluntary response sampling. Similar to convenience sampling. A voluntary response sampling is mainly based on ease of access. Instead of the researcher choosing participants and directly contacting them, people volunteer themselves. Example, by responding to a public online survey. Let's say you have an online survey and people are responding to it. One easiest example of voluntary response sampling is LinkedIn polls. If you are creating a post on LinkedIn and you are having a poll whether data analytics is the best domain or data science, and people start voting on them. That's kind of a voluntary response sampling. Next comes snowball sampling. If the population is hard to access, snowball sampling can be used to recruit participants via other participants. It is used where it is hard to find the potential population for research. For an example, you are researching experiences of homelessness in your city. You are working in a city, let's say Tokyo or Jakarta or any kind of cities you are from, and you are kind of researching experiences of homelessness in your city. Since there is no list of all homeless people in the city, probability sampling isn't possible. So you meet one person who agrees to participate in the research, and she puts you in contact with other homeless people she knows in the area. For example, you meet Mr. X and you talk to him or her that, hey, you know what, I want to talk to more homeless people in order to get some survey data. Now she gets in touch with you and she basically recommends you that I know some sort of people, homeless people who can help you out. So this kind of sampling technique is called as snowball sampling. That's all about the various non-probability sampling with examples. I'm pretty much sure that you now have a basic understanding on these topics. That's all about this video. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about the population sampling. What do you mean by population sampling? Analyzing or testing entire population is impossible and also a cost and time taking process. To save our money and time, we use the subset of the entire population called as sample. Population sampling is the process of selecting a subset of the objects that is representative of the entire population. The sample must have sufficient size of objects to warrant statistical analysis. Must be performed correctly since errors can lead to inaccurate and misleading result. Now this particular table will give you an initial idea about the mathematics behind it. You can see the first column, which is population or sample. The first category is population and the second category is the sample. There are various terms inside population: population size, population mean, and population variance. Similarly, we have sample size, sample mean, and sample variance. Now, before talking about variance, let's talk about standard deviation. Standard deviation. Well, I will have a detailed class on standard deviation in one of our future modules, in one of our future classes. But standard deviation simply means it's a measure of how spread out numbers are. It is usually symbolized with this, which is called as sigma, the Greek letter sigma. The formula of standard deviation is very simple. Standard deviation is nothing but the square root of variance. But what is variance? Variance is nothing but it is defined as the average of squared differences from the mean. Now, if you talk about this formula, variance is simply summation of xi minus mu square divided by n, where summation simply means the combination, the addition of all the values. Xi means the original data point, and this symbol, which is called as mu, is nothing but your mean value, or in simple terms is called as average. So variance formula is this. It is the summation of xi minus mu square divided by n. That's all about variance. Size basically means the number of items or elements in the population, and mean is the average value. If you closely look at the formula of population variance and sample variance, there is a minute difference in the denominator. In population, in the denominator we have n, but in sample we have n minus 1. The reason behind this will be explained in one of our future videos, but as of now, just remember this thing. Population variance is something like summation of xi minus mu square by n. If you have 100 records in your population, this n becomes 100. If there are 10 records in your sample out of population, then the variance becomes xi minus mu square by 10 minus 1, which will be 9. Okay. So that's all about this particular slide on population sampling. Well, I'll try to quickly explain a small example using the mathematical formulas. Let's say I have few records 5, 10, 15 and 20. What is the addition of these numbers? The addition of these numbers are, let's say one more, 30. 5, 10, 15, 20, 30. If I sum it up, it becomes 50, 55, 65. So it becomes 5 plus 10, 15 plus 15, 30, 80. So it becomes 80. Now 80 divided by 5, what will be the average value? It will be 16. Now what will be xi minus mean? For the first record, it will be minus 11. For the second record, minus 6. Third record, minus 1. Fourth record, 4. Fifth record, 14. What will be xi minus mu square? So this becomes 121. This becomes 36. This becomes 1. This becomes 16. And 14 square becomes, I think, 196. I hope everybody knows that the square of a negative number is always a positive number, right? So this becomes my xi minus mu square for each of these entities. What will be the sum of these values? So the sum of xi minus mu square will be 121 plus 36 plus 1 plus 16 plus 196. If you add it up, 196 plus 16 plus 1 plus 36 plus 121 becomes 370. So if these 5 records are part of my population, then the variance becomes summation of xi minus mu square divided by 5 root over. This becomes, sorry, not root over. If it is root over, this becomes a standard deviation. Let me write it down, standard deviation. Okay, which becomes 370 by 5 root over, which becomes 370 by 5 is simply 74. So 74 is my variance, and my standard deviation is the root over of 74, which is somewhere around 8 point something, 8.6. This becomes your standard deviation. Now, if these 5 records are a part of your sample data, not a part of your population data, in that case, the standard deviation formula becomes 370 divided by 4 root over. So 370 by 4 is around 92.5. Root over will be, 92.5. Root over is 9.6. 92.5 root over is 9.6. So here the variance becomes 92.5. The standard deviation becomes 9.6. So that's the mathematical way of understanding different concepts. Well, the why part is still not clear, but hold on, we have a separate video for that. That's all about this particular video on population sampling. And trust me, the mathematics and the all this kind of calculations part is going to be even simpler and simpler in our future videos as well. I'll try to simplify as much as possible. So that's it about this particular video. See you in the next video. Hi. Welcome to this module on statistics, and in this video we shall be talking about why do we have n minus 1 for the sample data and n for the population data. So far we already understood the formula of variance and standard deviation. Variance, which is nothing but standard deviation square, is nothing but summation of x minus mu square divided by n. Now this exact formula changes for the sample data. In case of sample data, the variance is nothing but summation of x minus mu square divided by n minus 1. Now, why do we have this n minus 1 for sample data and n for this population data? Well, there is a theory behind it. We have to take a small example and try to understand why do we have this. This is basically called as Bessel's correction. This method corrects the bias in the estimation of the population variance. It also partially corrects the bias in the estimation of the population standard deviation. The idea behind this is that this is a more unbiased measure of variance than the usual definition. Let's try to take a small example and try to understand why n minus 1 for sample and why n for population. Imagine you have a book shelf. Imagine you have a book shelf. Let's say the total thickness of the first 6 books. Imagine you have 6 books. Turns out to be 158 mm. So let's say here we have 158 mm as the total thickness, which definitely means the mean will be 158 divided by 6, which will be 26.3. That's my mean thickness. Now you take out and measure the first book's thickness, which is called as 1 degree of freedom, and that is 22 mm. Let's say the first book thickness was, let's say, 22 mm. Now you have 5 books. What is the total thickness of 5 books? It is 158 minus 22, which is 136 mm. Now we have 5 books. Now you measure the second book, which is second degree of freedom, and find it to be 28 mm. Let's say the second book is 28 mm. Now here, what will be the total thickness left? 136 minus 28, which will be 108 mm, and now you have 4 books. And the same process goes on. In this way, by the time you measure the thickness of the 5th book individually, which is here you are selecting the 5th book. When you are doing that, which is the 5th degree of freedom, you automatically know the thickness of the remaining 1 book. Let's try to take examples. Now, here we have 4 books and 108 mm. Let's say the third book is like 30 mm. Now here, the total width will be 78 mm and we have 3 books. Then the fourth book, let's say, is 25 mm. So here, the left out will be 53 mm and we have 2 books. Imagine at this point of time, where you have 2 books, the total thickness is 53 mm. Here you are picking the 5th book, and let's say the 5th book, which is called as the 5th degree of freedom, is found to be, let's say, 20 mm. When you find the thickness of the 5th book, it is quite understood that the 6th book, the final book's thickness, is going to be this minus this, which will be 33 mm. So you don't have to know about this final book. You are easily getting the final book's thickness when you are picking the 5th book. That means you automatically know the thickness of the 6th book, even though you have measured only 5. Extrapolating this concept in a sample of size n, you know the value of the nth observation, even though you have only taken n-1 measurements. That is, the opportunity to vary has been taken away for the nth observation. And exactly this is one of the reasons why we do not consider n in terms of sample data. So in sample data, we consider n minus 1. That's all about this particular video about why n minus 1 for sample data and why not n. And see you in the next video. Bye-bye. Hi, welcome to this module on statistics and this chapter on descriptive analytics and statistics. In this particular chapter, we are going to cover everything related to the descriptive part. There are majorly two concepts which is studied inside the descriptive statistics. One of them being measures of central tendency and one of them being measures of dispersion. Now these two topics are going to be the most important topics under descriptive, and we will be doing a deep dive analysis on these kind of topics. Under central tendency, we'll try to understand the concepts like mean, median and mode. And under dispersion, there will be concepts like range, interquartile range, variance, standard deviation, mean deviation, and so on. Each and every topic is going to be covered in details. So see you in the next video where we will deep dive into it. That's it. Thank you. Hi, welcome to this module on statistics, and in this video we shall be focusing on measures of central tendency. So far, we already know that statistics is of two types. One is your descriptive and another is your inferential. And inside descriptive comes this topic called as measures of central tendency. What exactly is measures of central tendency? As you can see, it measures the center value of the dataset. It gives us the idea about the concentration of the value in the central part of the distribution. In simple terms, a measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within the set of data. As such, the measure of central tendency is also called as measure of central location. They are also classed as summary statistics. The mean, often called as average, is the most likely measure of central tendency that we are most familiar with. We all know what exactly is mean, what is an average, right? Apart from mean, there are others as well, which includes median and mode. The mean, median and mode are all valid measures of central tendency. But under different conditions, some measures of central tendency become more appropriate to use than others. Now, what exactly is the usage of these topics? Why are we discussing these things? First of all, let's try to understand that each one of them is a central tendency, is a measure of central tendency, which gives us an idea about the central part of the distribution. Going forward, we have separate slides on mean, median and mode, where you will understand that using examples, we'll try to understand which type of concept is going to be used in which type of scenarios. So that's all about this particular video on the basics of measures of central tendency. Going forward, we have dedicated videos on mean, median and mode. That's about it. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about mean. Mean is nothing but the statistical definition or statistical term that we use instead of average. What exactly is average? We all know what is average. An average set of observation of the data. It computes the sum of all observation present in the data sets divided by the total number of observation. For an example, you have three numbers 1, 2 and 3. What will be the sum of these numbers? The sum will be 6. What will be the average of these numbers? The average will be 6 divided by 3, which becomes 2. Now this is nothing but your mean. So mean or average is nothing but add or sum each number or observation present in the data set, calculate the total number present in the dataset, divide sum of observation to the total number of observation. Using mathematical formulas, which looks really complicated, this is nothing but this x bar is nothing but your mean value. Mean value is nothing but sum of all x divided by n. This symbol is called as summation, which is nothing but sum of all numbers. So if you are passing x here, that means 1 plus 2 plus 3, which is 6. So in the numerator becomes 6 divided by how many entities? We have 1, 2 and 3, 3 numbers. So here the average becomes 2. So mean or average is the most popular and well-known measure of central tendency. It can be used with both discrete and continuous data, although its use is most often with continuous data. The mean is equal to the sum of all the values in the dataset divided by the number of values in the dataset. So if we have n values, in that case, and the values are x1, x2, x3, xn. So here the mean value will nothing but x1 plus x2 plus xn divided by n. And this is nothing but this particular formula. Okay. So summation of x divided by n. Now, when do we use mean? And why do we use mean? Where is the scenario where we start using this mean? Imagine a data set. Let's say you have a column called as age. You have a data. Let me just rub this off. You have you have a data set. And imagine one of the columns is age. And as you have captured the data, some of the records are null. Let's say one of these ages is 25, 29, null, 31, 25. So out of 5 members, one of them is a null record. Now, in your data analysis, while you prepare your data, handling missing values is one of the critical tasks that we handle. Because if you don't handle the missing values, your analysis could be, you could go in a wrong direction of your analysis. So it is usually recommended to deal with your missing values, which we will be covering in depth in the future classes while we talk about the exploratory data analysis. But what is the right way of imputing this value? One of the most idiotic approach is randomly impute it with some random numbers. Let's say impute it with 30. Is this a right approach? No. What is a better approach? A better approach is imputing using mean or median. So if you impute using mean here, what will be the mean here? 25 plus 29 plus 31 plus 25 divided by 4, which will be 25 plus 29, which is 54, plus 31 plus 25 should be 110 divided by 4, which is 27.5. Now, as this column is age, can somebody's age be 27.5? Well, logically it could be 27 years and 6 months. But as everything is a whole number without any decimals, probably we will use a rounded number here, which is 28. So 28 becomes my imputed values that we are imputing in the missing values. This is one of the applications of mean. That's all about this particular video on mean. I hope you understood what is mean, what is average. In the next video, we shall be talking about median, mode and various other topics. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about the second type of measures of central tendency, which is median. In simple terms, median is nothing but your middle number. That means the center number. found by ordering all data points and picking out the one in the middle. If there are two middle numbers, taking the mean of those two numbers will give you the median value. Mathematically speaking, there are two possibilities. If you have a set of numbers, you could have odd numbers or you could have even numbers. What do you mean by odd numbers? Let's say you have 5 numbers in this list. That means you have odd numbers. Now, if you have odd numbers, it is easily understood that the middle value is going to be the third number. But what if you have 6 numbers? Because in 6 numbers, you have 1, 2, 3, 4, 5, 6. Here there are 2 middle numbers. Now in this case, what happens is you have to take the average of these two. So mathematically speaking, the number of observations is odd. In that case, the median is the middle value, which is at position n plus 1 by 2. In case of even numbers, the median is the average of two middle values. Find the value at position n by 2 and then find the position at n by 2 plus 1 and then try to find the average. Well, sounds little bit tricky from the theoretical concepts point of view. Let's try to understand using an example. Let's say I have an example. Again, I have age. I have 25, 31, 27, 23, 33, 32. Now, how to find the median of these 6 numbers? How to find the mean of these 6 numbers? It is simple. Summation of all the numbers divided by n. Right? Which means it will be 25 plus 31 plus 27 plus 23 plus 33 plus 32 divided by 6, which is 28.5. This is your mean value. How to find the median? First of all, to find median, you have to order them. That means you have to sort them. Let's try to sort them. 23 comes first, then comes 25, then comes 27, then comes 31, then comes 32, then comes 33. As there are 6 numbers and it falls into this category, first we have to find n minus n by 2, which is the third value. 6 by 2 is third, this value. What will be n by 2 plus 1? It will be this value. Now we have to take an average of these two. So the average of these two will be 58 by 2, which will be 29. So 29 becomes your median. Imagine you have another number here. Let's say 19. Now if you sort it, 19 comes here. 1, 2, 3, 4, 5, 6, 7. Out of 7, we have to find n plus 1 by 2, which is 7 plus 1 by 2, which is the fourth location, which is 1, 2, 3 and 4. So this becomes my median when you have odd numbers. So this is the concept behind median. Now you must be thinking one question in your mind, that somehow median and median and mean are kind of similar concepts, but in which scenario do we use what? I will give you an example of what scenarios we do not use mean. The mean has one main disadvantage. It is a particularly susceptible to the influence of outliers. What if you have multiple staffs? Let's say staff number 1, 2, 3, 4, 5, 6 and so on. Now you have salary. So 15k, let's say 18k, let's say 16k, let's say 14k, let's say 90k and let's say 95k. Now the mean salary of these 6 people will be, if you try to calculate, the mean salary will be 15 plus 18 plus 16 plus 14 plus 185 is 248 divided by 6, which is 41k. Right? The mean is 41K. However, inspecting the raw data suggests that this mean value might not be the best way to accurately reflect the typical salary of a worker, right? Because if you analyze these four people, they are already in the range of 14 to 18. So this is not depicting the right numbers, because most of the people are within the range of 14 to 18K, right? The mean is being skewed by the too large salary. Now I used a term called as skewed. Well, we will be covering this topic in one of our future videos. Okay. Therefore, in this situation, we would like to have a better measure of central tendency. As we will find out later, taking the median is a better option. Now, what will be the median here in this case? If I sort the numbers 14, 15, 16, 18, 90, 95. So the middle value is these two. If I take a median, it will be 17 because the average is 17, right? Now this makes sense. If somebody asks you what is the median value, if you say 17K, it sounds okay because most of your employees are falling in the range of 14 to 18, right? So in these kind of scenarios, if you have outliers, in those cases, median is a better option to use. That's all about this particular session on median. In the next video, we shall be talking about mode, which is again another central tendency technique. See you in the next video. Hi, welcome to the module on statistics. In this video, we shall be talking about the third type of measure of central tendency, which is mode. What exactly is mode? The value which occur most frequently in the set of observation. Can have more than one mode, which is called as unimodal, bimodal or multimodal. What are the steps to find the mode? It's very easy to find mode of any observation. Take the most frequent value present in the data set. Special cases. If the maximum number of frequency repeated, if the maximum frequency is occurred at the beginning and end of the observation, if there is irregularities in the distribution. In all the above cases, we find the mode of the observation is using method of grouping. Let's try to understand using an example of where do we use mode. Mostly, mode is useful for categorical data. Imagine you have, again, I'll take an example. You are analyzing some customers' data. You have multiple columns. And one of these categorical columns is gender. Out of the 10,000 records or 1000 records that you have, in this particular example, we'll take 5 records. Let's say one is male, null, female, female, female. So you have 5 records. Imagine you have 5 records. I cannot simply write down 1000 records here. It is not possible. So example, we are taking 5 records. Let's say this is how the records looks like, and obviously you have one missing value. So what do you impute here? Idiotically, you cannot blindly impute male or female. Makes no sense, right? In this case, what we usually do is we find the mode here. As female occurrences are 3 and male occurrences is just 1, female becomes your mode. So a better value to impute here will be female. So this is one application of mode. This is where we use mode. But again, there are some drawbacks in the mode technique as well. What are the drawbacks? Simply try to understand this question, understand this scenario. Let's say you have 1000 records. And out of that, let's say you are analyzing gender. Out of these 1000 records, imagine 200 records are null values, or 200 gender records are null. Other than that, the 800 records that you have, let's say 640 are males and 160 are females. So what is the ratio here? The ratio here is almost 4 is to 1, right? 4 is to 1 ratio. Now, how do you impute these 200 records? The mode is very clear, the mode is male. But if you impute male in all the missing values, your ultimate records will be 840 male and 160 female. Now the ratio is changing from 4 is to 1 to 84 is to 16. Almost more than 5 is to 1 ratio, which is not in sync with the original distribution. So in these kind of scenarios, what we usually do is we try to maintain the ratio. The 200 records that we have, so what we will do is almost 160 records we will impute as male and 40 records we impute as female. But in certain scenarios where you have very less number of missing values, in that case you can also use mode. I hope everything is clear. These are all theoretical concepts. Once we jump into the practical sessions, once we jump into the EDA sessions, you will have better understanding, because we will be using some live data and we will be showing you different strategies of how do we use these concepts in real life. That's all about this topic on mode. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about measures of dispersion. In the last video we talked about measures of central tendency, where we understood the different concepts like mean, median, mode, and we also talked about various examples on where these concepts are going to be used. Well, in this video we'll stick to the dispersion part in statistics. What exactly is dispersion? Dispersion is the state of getting dispersed or spread. Statistical dispersion means the extent to which numerical data is likely to vary about an average value. In other words, dispersion helps to understand the distribution of data. Now, measure of dispersion indicates that how the data is dispersed from the measure of central tendency. In statistics, the measures of dispersion helps to interpret the variability of data, that is to know how much homogeneous or heterogeneous the data is. In simple terms, it shows how squeezed or scattered the variable is. Now, let's try to understand the different types of measures of dispersion. The first one is range. It is simply the difference between the maximum value and minimum value. For an example, 1, 3, 5, 6 and 7. Here the range is 7 minus 1, which is 6. It is simply the difference between the maximum value and the minimum value. Second comes variance. Variance deduct the mean from each data in the dataset, square each of them and add each square and finally divide them by the total number of values. Variance is basically termed as V, or else we can also term it as sigma square. What is sigma? We will try to understand it. Sigma square is nothing but summation of x minus mu square divided by n. Mathematically, we'll try to understand what exactly is this, but this is how the formula of variance is, where this particular symbol is nothing but which is summation. Here mu is nothing but the mean value. I hope everybody knows about mean, and x is your original attribute and n is the total number of entries. We also have interquartile range, which is called as IQR. Now this is nothing but Q3 minus Q1. What is Q3? Q3 is usually termed as the 75th percentile. Well, with examples we have this particular topic covered in the future videos, and Q1 is nothing but your 25th percentile. We'll mathematically understand each one of them. And then comes standard deviation. Standard deviation is nothing but the square root of variance. As I have already mentioned here, variance is nothing but sigma square. Now this sigma is nothing but your standard deviation. The square root of variance is known as standard deviation. So if I talk about the mathematical formula of sigma, this becomes sum of x minus mu square divided by n root over. And then comes mean deviation. The average of numbers is known as the mean, right? Now how much deviation is having from a particular mean, that's basically your mean deviation. Again, we have it covered in our future slides, nothing to worry about. That's all about the basics of measures of dispersion. We'll have our concepts more clarified in the future videos. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be discussing the first measure of dispersion, which is range. Somehow we already understood what exactly is the meaning of range, which is the difference between your maximum value and the minimum value. This is one of the simplest measure of dispersion. It measures the difference between the highest value and the lowest value present in the dataset. It is used to construct control chart in quality assurance. It is also useful when you want to focus on extreme values of the dataset. Now what if you have a data? Obviously you will have multiple columns in it. Let's say one of these columns is age. What if somebody asks you, can you tell me what is the range of age? Which basically means what are the lowest values and what are the highest values? What is the difference between them? If the age starts from 18 and it goes till 90, then the range here is going to be 72, which is highest minus lowest. So the formula of range is very clear. Range is highest value minus lowest value. Talking about an example, let's say I have values like this. What will be the range here? The minimum value here is 1. The maximum value here is 7. So the range here is going to be 7 minus 1, which is 6. That's all about this video on range. In the next videos, we shall be talking about the other dispersion techniques. Hi, welcome to this module on statistics, and in this video we shall be talking about the interquartile range, IQR. This is another measures of dispersion technique. But what exactly is this? This basically measures the middle 50% of the data. So interquartile range is a measure of where the middle 50% of the data is. Where a range is a measure of where the beginning and the end are in a set. We already covered range in the previous video. What is the minimum value and the maximum value? That gives you a range of the data. But IQR gives you the range of your middle 50%. So IQR formula is simply Q3 minus Q1. We'll try to understand what this Q3 and what this Q1 means using an example. This indicates how the data is dispersed around the mean. It is usually the difference between the third quartile and first quartile value of the dataset. It is helpful to detect the outlier present in the dataset. Formula is clear, Q3 minus Q1, but let's try to understand how do we calculate Q3 and Q1. Let me start with an example. Let's say I have an example and I have numbers like 1, 2, 5, 6, 7, 12, 9, 15, 18, 19 and 27. Now simply if you want to find the median, let's say we want to find the median, the first thing that we need to do is going to be calculating the median, right? So we have to sort these values first. How do we sort these values? 1, 2, 5, 6, 7, 9, 12, 15, 18, 19 and 27. So what will be the median here? the median is here going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 means 11 plus 2 by 11 plus 1 by 2, which is the sixth position. So 1, 2, 3, 4, 5, 6. So 9 becomes your median. Now let's try to place some parentheses here. So 9 is your median value, right? The median value. So median helps you to spot your Q1 and Q3 easily, right? Now, how do we find Q1 and Q3? Think of Q1 as a median in the lower half and think of Q3 as a median in your upper half. So what will be the median here? The median here is going to be 5 and the median here is going to be 18. Now if you subtract 18 minus 5, which makes it 13, that is basically your IQR. Now what if you have an even set of numbers? We'll try to take another example here. Let's say we have even set of numbers. Let's say 3, 5, 7, 8, 9, 11, 15, 16. How much? 1, 2, 3, 4, 5, 6, 7, 8. Let's say we'll take two more numbers, 20 and 21. They're already sorted. Now make a mark in the center of the data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So somewhere here, right? Place the parenthesis around the numbers above. So the parenthesis comes here. Now what will be my Q1 value here? The Q1 value will be 7. The Q3 value will be 16. Now what will be Q3 minus Q1, which becomes 16 minus 7, which becomes 9. So 9 is basically your IQR. Now I hope that you got a fair amount of understanding about IQR, which is Q3 minus Q1. So be it odd number of values or even number of values, identifying Q3 and Q1 is very simple, and just subtract Q3 minus Q1, which will give you IQR. That's all about this particular video. In the next video, we shall be talking about some other measures of dispersion. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about our next measure of dispersions, which is variance and standard deviation. We are going to cover both these topics in this video because they are related to each other, mathematically and conceptually. Now what exactly is variance? Simply, variance is a type of dispersion technique. Measures the dispersion of the data around the mean of the data. It indicates how the data is dispersed from its mean value. If the value of variance is low, that means it is closer to the mean value. So it's called as low variance. That means if the variance is closer to the mean value, which is called as a low variance scenario. If there is significant difference in the value from the mean, then it is called as high variance. Variance is often denoted by V, or we also denote it using sigma square. This is basically sigma, which is otherwise called as standard deviation. What exactly is standard deviation? Standard deviation is one of the most important and frequently used method of dispersion. It is simply the square root of variance. It indicates how far away the data points are dispersed from the mean, and it is denoted by sigma. Now talking about the mathematical formula, this is how variance is denoted, and the formula is like this. If I simplify it, it is nothing but sigma square is the summation of xi minus mu square divided by n, where mu is nothing but your mean value, n is nothing but your number of parameters. Now this particular formula changes from n to n minus 1 if you are dealing with a sample. So in short, when you are dealing with population, the value is n. When you are dealing with sample, the The formula is n minus 1. Now let's try to take some examples and try to solve the variance. And same goes with standard deviation as well. Standard deviation is nothing but summation of xi minus mu square by n root over. So let's try to take some examples and try to understand what will be the formula of each one of them, as in using formulas, what will be the values. Let's say I have some numbers 1, 3, 5, 5, 6, 7, 9 and 10. What will be the mean value here? That means mu. The mean will be 1 plus 3 plus 5 plus 5 plus 6 plus 7 plus 9 plus 10 divided by 1, 2, 3, 4, 5, 6, 7, 8. Simple. Which will be 4, 5, 9, 14, 20, 27, 36, 46 by 8. 46 by 8 will be around 5.4075. 4607, 4820. Yeah, around 5.75. Let's try to validate it. 46 divided by 8. Yes, it is 5.75. Now this becomes my mean. Now, as we already know the formula, so this is my x. Let's say 1, 3, 5, 5, 6, 7, 9 and 10. My mean is 5.75. So while calculate the numerator first. So xi minus mean. That means 1 minus mean, which is minus 4.75, minus 2.75, minus 0.75, minus 0.75, 0.25, 1.25, 3.25, 4.25. Now I will calculate xi minus mean square. So these individual square values. What will be the square values? You can simply take a calculator and try to calculate it. 4.75 multiplied with 4.75, it is 22.56. 22.56. 2.75 multiplied with 2.75, it is 7.56. See, irrespective of the number being negative or positive, the square of that number is always positive, right? Similarly, we'll have 0.56. We'll also have 0.56. This will be 0.06, 0.0625 in short. This will again be around 1.25, 1.56. This will be 10.56 and this will be 18.06. Now what I will do is summation of xi minus mu square by n. We are calculating variance first. So my numerator will be sum of all these values. So we'll try to sum all these values. If you sum it up, the values will be, let's try to use a calculator, 22.56 plus 7.56 plus this plus this plus this plus this plus this should be around 61.5. Let's try to validate it. 22.56 plus 7.56 plus 0.56 plus 0.56 plus 1.56 plus 10.56 plus 18.506, 62.4. One second, let me just do it again. 22.56 plus 7.56 plus 0.56 plus 0.56 plus 0.06 plus 1.56 plus 10.56 plus 18.06, somewhere around 61.48. I have just rounded it up to 61.5. Now how many attributes do we have? 1, 2, 3, 4, 5, 6, 7, 8 divided by 8. This becomes 61.5 divided by 8, which becomes 7.68. If you round it off, it will be 7.69, around 7.69. Now this is your variance, right? Now what is the mean? You can see the mean is 5.75 and the variance is 7.69. That means the variance is almost very close to the mean, like the difference is less than 2, right? So it could be treated as low variance, but again, these are very few records we have. In real scenarios, when we analyze with thousands and thousands of records, that give us more idea, right? So here my variance is 7.69. So what will be my standard deviation? This will be the square root of this 7.69, which will be, let's take an example, let's take help from the calculator. It is 2.77. Now this becomes my standard deviation. So that is all about variance and standard deviation, very similar to each other. I hope everybody is clear about the definition point of view and from the mathematical point of view, right? Now, if these 10 records are not a part of your population and if they are part of your sample data, in that case your variance, which is sigma square, becomes, basically we do not consider it as sigma square. In case of sample, we consider it as s, which is, this is just a change in symbol, that's it. It is still the variance. This particular s is still the standard deviation, but it is the standard deviation of sample data, right? So this is nothing but 61.5 divided by 7, whatever the values are. 61.5 divided by 7, which is 8.78. Now what will be the standard deviation here? Root of 8.78, which is going to be 2.96. Okay, so try to memorize this thing. In case of population, it is always divided by n, and in case of sample, it is always divided by n minus 1. That's all about this particular video on standard deviation and variance. In the next video, we shall be talking about some other topics. See you in the next video. Hi, welcome to this module on statistics, and in this video, we shall be talking about mean deviation. What exactly is mean deviation? Simply, we could already guess what could be the meaning of this. Mean is definitely understood. Mean is the average of a set of numbers. And deviation somehow gives me an intuition that how deviated these values are from the mean value, right? So the definition of mean deviation is very clear. It is the average sum of the absolute values of the deviation from any arbitrary values, example mean, median or mode, etc. It is suggested to calculate from median because it gives us the least value when measured from the median. Talking about the formula, this is how the formula looks like. It is summation of xi minus mu divided by n, and the numerator has an absolute value. What do you mean by this absolute value? Absolute value is simply nothing but, let's say we talk about a number minus 5. The absolute value is 5. We do not worry about the minus or plus attribute of it. Be it 5 or minus 5, the absolute value is always going to be 5. It is always positive number. Now let's try to take a small example. Let's say we have 4 people. Let's say Jennifer. Let's say my name, Sat, Amelia, Oscar. These are the 4 people. Now, and one more person, maybe Mr. X or could be James, right? Now, Jennifer has 4 apples. I have 3 apples. Amelia has 3 apples. Oscar has 2 apples. And James has 5 apples. The question here is find the mean deviation of the data. Now, if you start adding the mean value, let's try to calculate the mean value. The mean value will be 4 plus 3 plus 3 plus 2 plus 5 divided by 5. It is 4 plus 3 7 plus 3 10 plus 2 12 plus 5 17 by 5, which is 3.4. So the mean value is 3.4. Now what will be the x minus mean value? Let me just draw it again. 4, 3, 3, 2 and 5. So what will be x minus mu value? Imagine mu value is 3.4. We don't have to imagine, we already know. So the first value is going to be 0.6 minus 0.4 minus 0.4 minus 1.4, 1.6. So 0.6 minus 0.4 minus 0.4 minus 1.4, 1.6. What will be the absolute value? All the positive numbers. 0.4, 0.4, 1.4 and 1.6. Now if I have to add this part, which is this numerical part, sum of all the absolute values. So this is going to be 0.6 plus 0.4 is 1, 1.4, 1.4 plus 3, which is 4.4. 4.4 is going to be your numerator value. So what is my mean deviation? It's going to be 4.4 divided by 5, which will be 0.840, 0.8. So it's going to be 0.88. So the mean deviation is going to be 0.88. So that's how mathematically we understand the mean deviation part. That's all about this particular video. In the next video, we shall be talking about the next topics. See you in the next video. Hi, welcome to this module on statistics and the chapter on probability. In this video, we shall be discussing about the agenda of our next few videos. What are we going to cover in probability? We'll get started with probability in the next video, where we will talk about what exactly is probability, what are the probability related theories, concepts, and the formulas. Why do we use probability? Once that is done, we'll move into the additional rule of probability. And then we'll talk about the independent events. Further, we'll also talk about cumulative probability and conditional probability. And last but not the least, we'll be covering what exactly is Bayes' theorem. That's all about this particular video on this agenda. In the next video, we'll get started with the actual topics where we will start talking about probability and various concepts related to probability. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about probability. What exactly is probability? Probability denotes the possibility of the outcome of any random event. The meaning of this term is to check the extent to which any event is likely to happen. For example, when we flip a coin, imagine we are flipping a coin in the air. What is the probability of getting heads? Now, when we are tossing a coin, there are two outcomes that are possible. It could be either heads or it could be tails. Now, what is the probability of getting a head? The probability of getting a head is 1 by 2, which is 0.5. That means there are 50% chances of getting head and there are 50% chances of getting tails. So the general formula of probability is number of favorable outcomes divided by the total number of possible outcomes. Now in this example, number of favorable outcomes is when you are getting head, which is 1. How many total possible outcomes are possible? 1 and 2, which is 2. And hence the probability here is 1 by 2. The probability is the measure of the likelihood of an event to happen. It measures the certainty of the event. So, if the trial is repeated number of times under homogeneous and identical condition, then the value of ratio of number of favorable cases to the total number of possible cases is called as probability. Now, when talking about probability, there are multiple scenarios, multiple keywords that we need to understand. Well, talking about probability, Probability is something that always lies between 0 and 1. So probability is always in between 0 to 1, which measure how likely an event to be occur. Now let's try to go through some of the jargon, some of the keywords that we usually term or toss while considering probability. One of the terms is trial. What exactly is a trial? Trial is each performance in a random experiment. What is an event? Outcome of trial is an event, which is termed as P of E. Sample space, set of all possible outcomes in a random experiment. And then what is a random experiment? To perform more than once. Now let's try to understand these terms using some examples. The first question that we will consider is going to be, what is the probability of getting an even when throwing a single die? Everybody knows what a die is. When we throw a die, the possible outcomes are 1, 2, 3, 4, 5 and 6. Now this becomes your sample space because these are all your possible outcomes. The event here is going to be getting an even number. My bad, getting an even number. Okay, so the event is here getting an even number. Now what are the possible even numbers? 2, 4 and 6. Here, what will be the probability of this occurrence? Considering this as A, the probability of A will be, the formula is number of favorable outcomes divided by the total outcomes. What are my favorable outcomes? It's going to be 2, 4, 6, which is 3, divided by total outcomes, which is 6, which becomes 3 by 6, which is 1 by 2. So the probability of getting an even number in a single die is 1 by 2. Similarly, what is the probability of getting a multiple of 5? So the sample space remains same. Here the event becomes multiple of 5. What will be my A here? It will only be 5 because 5 is the only element here which is a multiple of 5. So what will be the probability of A here? It will be 1 instance out of 6 instance. So the probability of getting a multiple of 5 is 1 by 6. Multiple of 3, 3 and 6, which is become 2 by 6, which is 1 by 3. Now considering another example. What is the probability of getting an head when tossing a fair coin? Let me rub this off. Getting an head when tossing a fair coin. So when you are tossing a fair coin, the sample space becomes head and tail. The event becomes getting an head. The A becomes H. The probability of A becomes favorable outcomes by total outcomes, which is 1 by 2. Now, this was a very simple example. Let's try to take a complicated example. What is the probability of getting 2 heads while tossing 2 coins? Let's try to understand the sample space. The sample space will be either heads heads or heads tails or tails heads or tail tails. The event will be 2 heads. The A will be HH. And the probability of A will be 1 divided by 4. So almost 25% chances are there to get 2 heads while tossing 2 coins. So the probability is 1 by 4. I hope you understood the basic concepts behind probability. There are multiple multiple things that we need to understand which comes under probability, which we will be covering in the next few videos. That's all about this particular video. See you in the next video. Bye. Hi, welcome to this module on statistics, and in this video we shall be talking about the addition rule of probability. In the previous video we talked about probability. We also talked about some of the examples on how to solve a probability problem, on how to understand the concepts of probability by using tossing a coin or taking the die examples. Now, coming back to this video where we will be talking about the addition rule of probability. There are majorly two rules, rule 1 and rule 2. The first rule is when two events A and B are mutually exclusive, the probability that A or B will occur is the sum of probability of each event. Now, one example would be, imagine you are rolling a die. Now the sample space of rolling a die would be 1, 2, 3, 4, 5 or 6. What if somebody asks you what will be the probability of getting either 2 or 5? Obviously there are two outcomes, right? So it will be 2 by 6, which will be 1 by 3. Now using this formula, what will be probability of A? That will be getting a 2, which is 1 by 6. Probability of B, which will be getting a 5, which will be 1 by 6. And if you add both of them, 1 by 6 plus 1 by 6, this becomes 2 by 6, which becomes 1 by 3. So this is an example of additional rule of probability, rule number 1. So when two events A and B are mutually exclusive, so here two events are mutually exclusive, getting a 2 or getting a 5 are mutually exclusive. In that case, the probability, which is probability of A union B, becomes probability of A plus probability of B. There is a small terminology alert, which is union. What is this union operation? I'm expecting people to know about this, but just in case you don't know, union operation is nothing but, we'll take an example and try to understand. Imagine A is something, let's say 1, 2, 3 and 4. B is something, let's say 2, 4, 6 and 8. Now if we draw A and B, this is A and this is B. What are the elements that are common in both 2 and 4? So this comes here. What are the elements present in A not in B, which is 1 and 3? What are the elements present in B not in A are 4 and 8. Universal value A union B becomes the entire data set, which is 1, 2, 3, 4, 1, 2, sorry, not 4 and 6, 6 and 8, 6 and, my bad. So 1, 2, 3, 4, 6, 8. This becomes your A union B. A intersection B will be only this part, which is common in both, which will be 2 and 4. Okay, just wanted to explain this concept because this is a mathematical symbol which basically means intersection. This means union. So here the probability of A union B will be probability of A plus probability of B. Talking about the second rule, when two events A and B are not mutually exclusive, the probability that A or B will occur is the sum of probability of each event minus the intersection of A and B. So your probability of A union B will be probability of A plus probability of B minus probability of A intersection B. Okay, this becomes your rule number 2. Now we'll take an example of both of these rules and try to understand. I think we already understood this example. I'll repeat once again. A single die is rolled. What is the probability of rolling a 2 or 5? There are two events happening, right? So there is a small mistake here. Please ignore that. So here the event of A occurring will be either 2 or 5. Okay. So the probability of A is getting a 2, probability of B is getting a 5. What will be probability of A? Getting a 2 will be only one instance, which will be 1 by 6. And probability of getting a 5 will again be one instance, which is 1 by 6. If you add them, this becomes 1 by 3, which we already understood in the previous slide. Now, talking about this question. In a math class of 30 students, how many students? 30 students. There are 17 boys and 13 girls. Okay. What is the probability of finding a girl from this? It will be 13 by 30. Clear? On a unit test, 4 boys and 5 girls made an A grade. How many made A grade? There were 9 students, 4 boys and 5 girls. What is the probability of choosing a girl or a student? So what is the probability of girl or A student? This will become probability of girl plus probability of A minus probability of girl and A. Sorry, yeah, and A. What is probability of girl? Which will be 13 by 30. What is the probability of getting an A grader? There are 9 A graders out of a class of 30. So the probability of getting A grade is 9 by 30. A probability of getting not A grade will be 21 by 30. So we will consider this 9 by 30 minus girl and A. How many girl and A? Which will be 5. 5 girls and A graders. So 5 by 30. This becomes minus 5 by 30. The overall equation becomes 22 minus 5, which is 17 by 30. Because this scenario is where the event A and B are not mutually exclusive. That's all about this particular video on the addition rule of probability. I hope both these examples, both these rules are clearly understood. That's all about this video. In the next video, we shall be talking about various other topics related to probability, and we'll try to take examples and help you out. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about independent events. In the previous video we talked about various probability concepts. Here we were going to discuss about the independent events. What are independent events? Well, if there is a concept of independent events, there definitely would be a concept like dependent events. Simply, independent events refers to the occurrence of one event not affecting the probability of another event. When two events A and B are said to be independent if any of these following equivalent statements hold. P of A upon B is probability of A, probability of B upon A is probability of B. Generally speaking, this is what the multiplication rule of independence says. The probability of A and B occurring is going to be probability of A multiplied with probability of B. Two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Now, one of the classic examples. What if you are riding a bike? Riding a bike. Another event is and watching a movie on laptop. Watching a movie on laptop. Now these are completely two different events and are independent of each other. Similarly, rolling a die and tossing a coin. These are definitely two different events. I'll try to frame a question so that we can try to solve this. The question is, what is the probability of getting an even number while rolling a die and getting a heads while tossing a coin? While you are rolling a die, the sample space, so this is your event A, now this is your event B. The sample space for event A while rolling a die is 1, 2, 3, 4, 5, 6. My event A getting even number is 2, 4 and 6. The probability of getting A here is 3 by 6, which is 1 by 2. In this case, the sample space is head and tails. The event A occurring, which is getting a heads, is 1. The probability of A or probability of B, let me write it as B so that we can reduce the confusion. Probability of B this will be B, probability of B will be 1 by 2. What is the probability of getting an even number and getting a heads together? So the probability of A and B, sorry, my bad. The probability of A and B. So the symbol here is going to be A and B. So the probability of A and B is going to be probability of A multiplied with probability of B, which is 1 by 2 multiplied with 1 by 2, which is 1 by 4. So probability of getting an even number and getting a heads is 25%. Because these two are independent events, they don't have dependency on each other. So one of the examples is that, as I told you, riding a bike and watching a movie on a laptop, studying hard for the exam and hitting 6 in cricket. They have no resemblance, they have no dependency. Studying hard or not is one event, hitting a 6 in cricket is another event, or scoring a goal in football is another event. Those are completely two different events and are called as independent events. So that's all about this particular session on independent events. See you in the next video where we will be talking about various other concepts. Thank you. Hi, welcome to this module on statistics, and in this video we shall be talking about cumulative probability. By far we already know what exactly is probability. Now, what is cumulative? The simplest definition of cumulative is something which is increasing or increased in quantity, degree or force by successive additions. Well, cumulative probability refers to the likelihood that the value of a random variable is within a given range, and this range is defined here. Probability of x within the range of a and b. So here x is a random variable and a and b are the range limits. Sounds a little bit confusing, but let's try to understand using this example. Consider a coin flip experiment. If we flip two coins, what will happen? So considering the two coins to be fair coins, if we consider flipping two coins at a time or tossing two coins at a time, the sample space is going to be head head, head tail, tail head and tail tail. These are the four possibilities while tossing two coins. Now what is the probability that the coin flips would result in one or fewer heads? That means your output has to be at least one or fewer heads. Could be zero heads also. So 0 head is this and 1 head is this. So definitely the probability becomes 3 by 4. But let's try to solve it using cumulative probability. The requirement is very clear. What is the probability that the coin flips would result in one or fewer heads? So of event X happening, one or fewer, less than or equals to 1. This is what we need to find out. And what is this? This is nothing but P of x equals to 0 plus P of x equals to 1. X equals to 0, that means 0 heads. That means one instance, 1 by 4. One head, that means two instance, which is 2 by 4. And now if I add it, it becomes 3 by 4. Now this is a typical example of cumulative probability. When somebody asks you something like this, can you tell me what will be the probability for getting one or fewer heads? Or if you are rolling a die, what is the probability that the addition of the number, let's say you are rolling two dice. If you are rolling two dice, obviously if you are rolling a single dice, these are the six entries possible, right? If you're rolling two dice, it could be 36 entries. 1 1 1 2 1 3 dot dot 1 6, again 2 1 2 2 dot dot 2 6, and it goes on till 6 6, right? What is the probability that the addition of both these numbers are less than equals to 5 or less than equals to 3 for simplicity? That means the addition of both the numbers could be 1, which is the minimum. The addition of two numbers could be 2, or addition of two numbers could be 3. Again, this is not possible, right? 1 0 or 0 1 is not possible. These are the two possibilities. X equals to 2 will be only one instance, which is 11. X equals to 3 will be 21 and 12. So there are 3 instances out of 36, which is 1 by 12, right? So this is an example of cumulative probability, right? So that's all about this particular example of cumulative probability. In the next video, we shall be talking about various other topics. See you in the next video. Hi, welcome to this module on statistics, and in this video, we shall be talking about conditional probability. Simply, conditional probability is the probability of one event occurring with some relationship to one or more other events. The formula that we use in conditional probability is probability of B given A is true is nothing but probability of A intersection B divided by probability of A. Now, conceptually or formula wise, I think this should not be a difficult formula to memorize, but we'll try to take help of examples and see how this formula can be used in real life. There are some other rules of multiplication as well. Probability of A intersection B is probability of A given B is true multiplied with probability of B, or else other way around, probability of B given A is true multiplied with probability of A. Let's try to take an example, and without looking at the solution, let's try to solve it. An urn contains 6 red marbles, and 4 black marbles. Okay. 2 marbles are drawn without replacement from the urn. That means if you pick it, you cannot replace it. What if replacement is allowed? There are two chances, there are two possibilities. Let's try to talk about if replacement is allowed. That means the first ball could be red or black, and whatever it is, it goes back to the urn, and again the second ball is picked, which could again be red or black. So here the probability of getting a black is 4 by 10. Here the probability of black is getting 4 by 10. So if replacement is allowed, the possibilities of 2 marbles to be black would be 4 by 10 multiplied with 4 by 10, which is 16 by 100, which is 0.16. As without replacement is mentioned here, that means this is not a scenario. That means if I consider 6 red and 4 black, in the first pick there are two chances. It could be red, it could be black. What is the possibility of a black marble? It is 4 by 10 and this is 6 by 10. Right? If it is a black marble, then in the next pick, 1 is gone from here. So this becomes 3. So 3 by 9 is the possibility of black marble. So combined together, the chances of getting two blacks where replacement is not allowed will be 4 by 10 multiplied with 3 by 10, which will be 12 by 90. Again, you can just further do the decimal calculations. Now, this is something where we haven't used formulas, but looking at the formulas, we are actually following the conditional probability rule. Let's say the A is nothing but the event that the first marble is black. What will be the probability of A? It will be 4 by 10. Let B the event that the second marble is black. As replacement is allowed, here it will be 3 by 9. In the beginning, there are 10 marbles in the urn, 4 of which are black. So probability of A becomes 4 by 10. After the first selection, there are 9 marbles left. So 3 of which are black. So probability of B given A is true is 3 by 9. So using the basic rule of multiplication, the probability of getting black and black, black in the first pick and black in the second pick, is this part. So this becomes this. Now take this one as an example. This is probability of B upon A is nothing but probability of A intersection B divided by probability of A. Simple, which is nothing but if it goes this way, so it becomes probability of A intersection B is nothing but probability of B given A is true multiplied with probability of A. So what is B given A is true? If A is true, that means somebody has already picked a black marble. In that case, what is the probability of B given A is true? This is 3 by 9 multiplied with probability of A. That means in the first pick, it has to be a black marble. So it becomes 4 by 10. So this becomes 12 by 90. So if you further simplify it, it becomes 0.133. So this is an example of conditional probability. Similarly, we'll take another example. In a group of 100 people, 40 bought sports drinks, 30 purchased snacks, and 20 purchased sports drinks and snacks. The question here is, if a buyer chosen at random bought a sports drink, what is the probability that they also bought snacks? Let's try to solve it line by line. Probability of A, which is buying a sports drink, is 40 out of 100, which is 0.4. Probability of A intersection B. A intersection B is nothing but the intersection of A and B, both happening together. It is also mentioned in the question. This will be 20 by 100, which will be 0.2. Now, using the mathematical rule that we discussed, we have to find if a buyer chosen at random bought A, which is bought a sports drink, what is the probability of buying snacks? So, probability of B given A is true, which is nothing but probability of A intersection B divided by probability of A, which is 0.2 divided by 0.4, which becomes 0.5. So the probability of buying snacks, probability that a person buys snacks given that he already has sports drink, is almost 50%. If we want to do the Venn diagram for this, let's say sports drink and snacks, we already know the numbers. This is 40, this is 20, and this is 30. So I hope everybody is clear. So if a buyer chosen at random bought a sports drink, what is the probability that they also bought snacks? So this is an assumption to be true. What will be the probability of this? So probability of B given A is true is going to be 50%. That's all about this particular topic on conditional probability. In the next video, we shall be talking about Bayes theorem. That's all about this particular video. See you in the next video. Bye bye. Hi, welcome to this module on statistics, and in this video we shall be discussing about Bayes theorem. What exactly is Bayes theorem? Bayes theorem is an extension of conditional probability. Conditional probability, I hope everybody has already gone through the videos. Conditional probability helps us to determine the probability of A given B, denoted by P of A given B. Bayes theorem says if we know probability of A given B, then we can determine probability of B given A, or vice versa. So as we already know, probability of B given A is nothing but probability of A intersection B divided by probability of A. In other words, probability of A intersection B is nothing but probability of B given A is true multiplied with probability of A. So the formula of Bayes theorem is basically the probability of A upon B, or A given B is true, is nothing but probability of this divided by probability of B. And if I use this formula here, this becomes probability of B upon A multiplied with probability of A divided by probability of B. So this becomes my entire formula for Bayes theorem. Probability of A given B is true is nothing but probability of A multiplied with probability of B upon A is true divided by probability of B. That's all about Bayes theorem. Now let's try to take some examples and try to understand what exactly and how exactly we solve Bayes theorem problems. So let's say this is an example, a bag X contains 4 white and 6 black balls. So let me draw X contains 4 white and 6 black balls. While another bag Y contains 4 white and 3 black balls. One ball is drawn at random from one of the bags and it is found to be black. So the probability of finding a black object or a black ball from X is going to be 6 by 10 individually, and here it's going to be 3 by 7, which should be clear. Let's say you pick one of the balls from either of these bags and found to be black. Find the probability that it was drawn from bag X. Now this is an interesting question. Let E1 be the event of choosing bag. So E1 be the choosing event of choosing bag X. Similarly, E2 be the event of choosing bag Y. Then probability of E1 is nothing but probability of E2, right? So choosing a bag, it could be X bag or it could be Y bag. Probability of choosing individual bag is 1 by 2. Also, probability of A upon event 1 is true is nothing but probability of drawing a black ball from bag X. Now this is 6 by 10. Similarly, the probability of A upon E2 is true. That means probability of black from bag Y is 3 by 7, which should be clear. By using Bayes theorem, the probability of drawing a black ball from bag X out of two bags. So probability of event E1 upon A is true is nothing but probability of E1 multiplied with probability of A upon E1 divided by probability of E1 multiplied with probability of A upon E1 plus probability of E2 multiplied with probability of A upon E2. This will be 1 by 2. Probability of E1 is 1 by 2. Multiplied with E upon E1 is 6 by 10. Divided by again 1 by 2. Multiplied with 6 by 10. Plus 1 by 2 multiplied with 3 by 7. This becomes 6 by 20 divided by, it becomes 6 by 20 plus 3 by 14. 6 by 20 plus 3 by 14. 6 by 20 divide by, let's try to solve this part. This will be, let's say, 7 to 10, 70, 140. Let's say 140 in the denominator, 7, 6, 42. I could be minutely wrong, but I'm trying my best not to be wrong. So taking 140 in the denominator multiplied by 7, 6 multiplied with 7 is 72, and then multiply with 10, which is 30, which is 72 by 140. 72 by 140. This becomes 6 by 20 multiplied with 140 by 72. 0, 0 cancelled, 2 cancelled, 7, 6 cancelled, 12. So this becomes 7 by 12. So the probability that it was drawn from bag X is going to be 7 by 12. So that's all about this particular concept on Bayes theorem. It's a very important concept that will be used in many of your future topics as well. One of the most important theorems in the field of probability and statistics. That's all about this particular session. We'll see you in the next video. Thank you. Hi, welcome to this module on statistics. In this chapter, we shall be focused on probability distribution. What exactly is probability distribution? In probability theory and statistics, a probability distribution is the mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. It is a mathematical description of a random phenomenon in terms of its sample space and probabilities of events. For instance, if X is used to denote the outcome of a coin toss, in that case, the probability distribution of X would take the value of 0.5 for probability of X equals to heads and 0.5 for probability of X equals to tails, considering that the coin is fair. Examples of random phenomena include the weather conditions at some future date, height of a randomly selected person, the fraction of male students in a school, the results of a survey to be conducted, etc. etc. There are many types of probability distribution. In this particular session, in this particular chapter, we shall be talking about each one of them. We'll get started with uniform distribution. Then we will talk about binomial distribution, Poisson's distribution, and normal distribution. At the last class, we will also talk about some of the feature scaling techniques, and we will see how scaling can be done for normal distribution and how can we convert a normal distribution to a standard normal distribution. So these are the topics that we will be covering in this particular chapter. See you in the next video where we will be jumping into each one of them. Thank you. Hi, welcome to this module on statistics, and in this video we shall be talking about uniform distribution. Now what exactly is uniform distribution? Simply, in probability theory and statistics, the continuous uniform distribution or rectangular distribution is a family of symmetric probability distributions. Majorly, uniform distribution is of two types: discrete uniform and continuous uniform. Let's try to understand each one of them, and then we'll probably take an example and help you out. In layman's term, each integer value between A and B has the same possibility to happen. Everybody knows the meaning of discrete and continuous variables. So if we know what is discrete and what is continuous variable, then understanding this concept won't take that much of time. In simple terms, the probability of X happening is 1 by n. Take an example of throwing a dice. When you throw a dice, let's the event be throwing a dice. When you throw a dice, what will be the sample space? The sample space will be, it could be anything, 1, 2, 3, 4, 5 and 6. What is the probability of getting 1? It is 1 by 6. Probability of getting 2, 1 by 6 and so on. So in short, the probability of getting each and every number is individually 1 by 6. If I start drawing, you will probably end up a diagram like this, where A and B are your events. It could be 1, it could be 2, it could be 3, 4, 5 and 6. Imagine there is another line for 5. And in your y-axis is always your probability of x, which is 1 by n. In this case, the n is 6, so this value is nothing but 1 by 6. That is your discrete uniform distribution. Now, what exactly is continuous uniform distribution? In layman's term, any values, integer or decimal values, between A and B has the same possibility to happen. The only difference between discrete and continuous is that here you only have the discrete values. Let's say there is something like this. Here you only have discrete values. What is the probability of 2? The probability of 2 will be 1 by 6. What will be the probability of 4? It will be 1 by 6. Can we have a number like 2.5 or 3.4? What is the probability of getting 3.4? Not possible, because 3.4 itself is not a part of the sample space because of the discrete nature of the data. So in continuous uniform, it could literally be any number. In layman's term, any values, integer or decimal values between A and B has the same possibility to happen. So now let's say we have a number A and we have a number B and the data is continuous data. So what will be the probability? The probability, I'm talking about continuous, the probability of X lying between A and B is basically 1, right? This entire box is going to be 1. The probability is going to be 1. That means if there are n number of continuous objects, you can imagine each probability accumulated value will be 1, right? Each probability value will be like 1 by something, and accumulation of each continuous variable ultimately will lead to 1. So this statement holds true, right? Now, as you can see, if I name it something like A, B, C and D for an example, this becomes a rectangle. What will be the area of this rectangle? The area will be height multiplied with length. So area becomes height multiplied with width or length, right? So what will be height? What will be the length? The length will be b minus a. B minus a. And we already know that the entire area is 1. So height multiplied with b minus a is 1, which means height is equals to 1 by b minus a. And that is the reason we have mentioned here the height as 1 by b minus a. Simple. In this case, in continuous uniform distribution, the mean is usually a plus b by 2, which is similar to your median as well, which is somewhere here, right? Imagine there is a scenario, for example, I'll try to rub this off, and probably let's say somebody asks you what is the probability of falling between C and D. So what will be the probability of falling between C and D? It is nothing but height multiplied with length. What is the length? It is D minus C. D minus C. What is height? Height is going to be constant, 1 by B minus A. So 1 by B minus A. So the probability here will be D minus C divided by B minus A. Usually in the case of uniform distribution, as I already told you, mean is nothing but A plus B by 2, which is similar to your median, and your standard deviation is nothing but square root of B minus A square divided by 12. That's all about uniform distribution. Let's go ahead and talk about an example which we already discussed. So if you are rolling a die once, the probability of each of the possible outcomes, that is 1, 2, 3, 4 or 6, is even, which is 1 by 6. The probability of getting 1 is 1 by 6. Probability of getting 2 is 1 by 6. So the probability is constant of whatever values you pick from the sample space. So this is how your uniform distribution looks like. For each and every value from 1 to 6, the probability is 1 by 6, which is almost 0.8, 0.18, I think. If I talk about 1 divided by 6, 0.17, 0.17, right? Almost close to 0.2. And this is throughout 0.17, 0.17, 0.17, and so on. Hi, welcome to this module on statistics. In this video, we shall be talking about the binomial distribution. What exactly is binomial distribution? The binomial distribution is a probability distribution used in statistics that summarizes the likelihood that a value will take one of two independent values under a given set of parameters or assumptions. The underlying assumptions of the binomial distribution are that there is only one outcome for each trial, that each trial has the same probability of success, and that each trial is mutually exclusive or independent of each other. Let's try to understand binomial distribution using a small example. Imagine you are tossing 5 coins. Obviously, when you toss a coin, the outcomes are head or tails. So imagine you are tossing 5 coins. So how many outcomes will be there? Let's say all 5 heads, or it could be 5 tails. It could be 3 head and 2 tails. It could be head, tail, head, tail, head, and it could be many other combinations. In short, there will be 32 combinations that are possible while you toss 5 coins. How is that possible? For the first coin, the possibilities are 2 times. Either it is head or tails. For the second coin, again the possibilities are 2, and it goes on till the fifth coin, which becomes 2 to the power of 5, which is nothing but 32. So if I talk about the sample space, I cannot write down, but there are 32 sample spaces, like 32 times. It could be combination of HTT, HT, HT, HHT, HHH, HH, TTT, something like that, right? Now, let's say my X here is finding the number of heads. What if I want to have what is the probability of finding 0 heads? Finding 0 heads, there is only one scenario which is TTT, which is 1 out of 32. So probability of x equals to 0 is going to be 1 out of 32. Let's try to take to the go to the next page and try to do a writing here itself. So I'll quickly write down again. My x here is number of heads, and I'm tossing 5 coins. So what are the total probability? The possible outcomes is nothing but 2 multiplied with 2 multiplied with 2 multiplied with 2 multiplied with 2, which is 2 to the power of 5, which is 32. These many possible combinations, right? Now what is probability of x equals to 0? That means when you have 0 heads, so that's only one case, right? If all the coin are having tails, tail, which is 1 out of 32 instances, right? Formula wise, it is nothing but 5C0 divided by 32. What is 5C0? 5C0 is simply 5 factorial divided by 0 factorial multiplied with 5 factorial multiplied with 1 by 32, which is 5 factorial cancel, 0 factorial is 1, which becomes 1 by 32. Similarly, let's say you ask me what is the probability of getting one head. Now it could literally be this H T T T T, or it could be T H T T T, or it could be T T H T T. It could be H here or it could be H here. Literally there are 5 combinations: T T T H T and T T T T H, right? There are 5 combinations, which should be 5 by 32. Using formula, we will just use n c of x, which is 1, divided by 32, which is 5 factorial divided by 1 factorial multiplied with 5 minus 1 factorial multiplied with 1 by 32, which is 5 factorial divided by 4 factorial multiplied with 1 by 32. 1 factorial is always 1. 5 minus 1 factorial is 4 factorial. So what is 5 factorial? 5 factorial is simply 5 into 4 into 3 into 2 into 1. And 4 factorial is 4 into 3 into 2 into 1 multiplied with 1 by 32. Everything is cancelled. 5 remains, which is 5 by 32. Similarly, if you go ahead for p x equals to 2, 5c2 divided by 32, which is 5 factorial divided by 2 factorial, 3 factorial into 1 by 32. 5 factorial, 3 factorial cancelled out. It remains with 5 cross 4. 2 factorial gets cancelled out here. So it becomes 10 by 32. Similarly, px equals to 3 will also be 5c3 by 32, which is again 5 factorial divided by 2 factorial, 3 factorial into 1 by 32, which is again going to be 10 by 32. And probability of x equals to 4 is again going to be 5 by 32, and probability of x equals to 5, that means all the 5 cases it has to be heads, which is going to be 1 by 32. Simple. Now that's all about the 5 different combinations of getting the number of heads. If I use this technique and start plotting, so let's say this is my 10 by 32, let's say this is my 5 by 32, 1 2 3 4 5, and this is 1 by 32, right? So 0 1 2 3 4 5. So at x equals to 0, it's going to be 1 by 32. At x equals to 1, it is 5 by 32, something like this. And then it is 10 by 32, and then again 10 by 32, and then this, and then this. Something like this, right? This is how the graph looks like. And this is your binomial distribution. If I quickly draw this diagram like this, it was not that accurate, but somehow, let me just redo it. Something like this, right? Now, this graph is nothing but a normal distribution graph. Like it looks like the bell curve, right? Normal distribution. But normal distribution is usually meant for continuous data. Here we are analyzing discrete data. 1, 2, 3, 4, 5. These are discrete data. So in short terms, binomial distribution is nothing but a version of normal distribution for discrete data. For continuous data, we call it as normal distribution. So definitely we'll have a class on normal distribution to understand more about it. But this is how your binomial distribution looks like. The internal graph which has been formed up looks similar to a normal distribution or a bell curve. The formula of binomial distribution is pretty much clear. The probability of x is nothing but nc of x, p to the power of x multiplied with 1 minus p to the power of n minus x. Okay, so we'll take another example and we'll try to solve it using this formula, because here I have somehow used this formula but it's not quite visible because it was a simpler example of 5 coins. We'll try to take a difficult example and try to implement this particular example and to implement this particular formula. So talking about this example, a coin is tossed 10 times. What is the sample space? 2 to the power of 10. Imagine whatever it is. 2 to the power of 5 is 32. 64, 128, 256, 5112. It should be 1024. If I am not wrong. 1024. This is my sample space. These many combinations are possible. Let's not go into that direction. What is the probability of getting exactly 6 heads? So we need to find probability of x equals to 6. Here x is getting a head. Simple. X is getting a head. We want to find probability of x equals to 6. How many trials do we have? The n value is here 10, right? X value is 6. Simple. The what is the probability of success? That means getting a head. Probability is 0.5, which is 1 by 2. Probability of failure is q, which is again 1 by 2. Using binomial distribution, we'll try to use this formula. N C x p to the power of x 1 minus p to the power of n minus x, which becomes 10 c 6 0.5 to the power of 6 0.5 to the power of 4, which becomes 10 factorial divided by 4 factorial multiplied with 6 factorial multiplied with 0.5 to the power of 10, in short, right? If you try to solve this, 10 factorial 6 factorial cancelled out, which should be left out with 10 9 8 7 divided by 4 3 2 1 into 0.5 to the power of 10. It gets cancelled out. 2 3 gets cancelled out. 3 2 gets cancelled out. 5. So 5 into 3 15, 230 into 7 210 multiplied with 0.5 to the power of 10. If you go ahead and calculate it, you will probably land up this number, which is 0.2. So the probability of getting exactly 6 head is 0.2. I hope everybody is clear with this formula. It looks very complicated, but it is very simple. NCX is nothing but n factorial divided by n factorial, sorry, divided by x factorial multiplied with n minus x factorial. This is what it is meant by this one. That's all about this particular session on binomial distribution. In the next class, we will be talking about normal distribution and various other topics. See you in the next class. Bye bye. Hi, welcome to this module on statistics, and in this video, we shall be talking about Poisson distribution. Poisson distribution is a type of probability distribution. In fact, it is a discrete probability distribution. The discrete probability distribution of the number of events occurring in a given time period, given the average number of times the event occurs over that time period. Let x be the discrete random variable that represents the number of events observed over a given time period. Example, calls per hour at a call center. Let lambda be the expected value or the average value of x. Example, the average number of calls received in a call center is 10. So your lambda value is 10. If x follows a Poisson distribution, then the probability of observing x events over the time period is this. Probability of x equals to x, lambda to the power of x multiplied with e to the power of minus lambda by x factorial, where e is nothing but your Euler's number, which is 2.718. Let's go ahead and take an example. We'll take the same call center example. The average number of calls for a call center per hour is 10, so lambda equals to 10. The probability of having different number of calls in an hour could be calculated as this. The probability of 0 calls, following the same formula, lambda to the power of x e to the power of minus lambda by x factorial, we will replace the x value as 0 and lambda value as 10. If you replace, you are going to get the probability value as 0.0045%. If you want, you can keep on doing for 1 call, for 2 call and so on. Arbitrarily, I have done the probability for 3 calls. Again, using this formula where lambda is 10 and x is 3. And if you replace these values, the value is coming as 0.75%. And you can see there is a steady increase in the probability value till 10 or 11 calls. What will be the probability of getting 20 calls? X equals to 20. I will use the same formula, lambda to the power of x, which is 10 to the power of 20, multiplied with e to the power of minus 10, divided by 20 factorial. Now, if you go ahead and use a calculator and calculate this value, the value is going to be almost 0.001, which is around, if you multiply 100, which is around 0.1%, almost. So this is how your Poisson distribution looks like. So probability of 0 calls is here, probability of 1 call, 2 call, and you can see the probability keeps on increasing till a certain extent, and then again it started decreasing. And this is the property of Poisson distribution. That's all about this particular topic on Poisson distribution. See you in the next video about other topics. Till then, bye-bye. Hi, welcome to this module on statistics, and in this video we shall be talking about normal distribution. What exactly is normal distribution? Well, before getting into the topic, let's try to talk about the other names of normal distribution. Normal distributions is also called as Gaussian distribution. And as the distribution looks like this, it is also called as Bell's curve. It looks like a Bell's curve. So normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. Graphically, normal distribution looks like a bell curve, as I already mentioned. And it is important in statistics and is key to the central limit theorem. What exactly is the empirical rule? The empirical rule basically tells us that if this is how our normal distribution looks like, for all normal distributions, 68.2% to be very precise, but let's assume 68%, almost 68% of the observations will appear within plus or minus one standard deviation of the mean. What does this mean? Normally, in a normal distribution, the center is usually the mean value. What is mean value? Mean is simply the average of all the numbers that we have. If I have 1000 records, and if let's say I'm analyzing age, that means for all these 1000 records, whatever mean I will have, that is this. Again, on these 1000 records, let's say I want to calculate the standard deviation, which we already studied in one of our previous classes. Standard deviation is nothing but, the formula of standard deviation is summation of xi minus mu square divided by n, and usually this formula is for population data, and obviously the denominator becomes n minus 1 for sample data. We already covered all these concepts. I hope it's kind of a refresher to you right now. Now mu is calculated, sigma is calculated. Usually this is your mu. This is usually your mu plus sigma and mu minus sigma. And it is told that the total percentage of data in this particular area is around 68%. 68.2% to be very precise. Similarly, if I start plotting mu plus 2 sigma and mu minus 2 sigma, usually this range is 95.4%. 95.4%. You can see, we'll try to ignore this image and let's try to focus on this image. This is your mu. Mu minus sigma, mu plus sigma. What is in this range? 68.2%. Mu minus 2 sigma, mu plus 2 sigma. What is in this range? Is 95% of the data. Mu minus 3 sigma, mu plus 3 sigma, 99.7% records. Now, as per normal distribution, it says that if the data is following the normal distribution, that means 68% of the data lies between mu plus minus 1 standard deviation. 95% lies between mu plus minus 2 standard deviation, and 99.72% of the data falls within plus minus 3 standard deviation. What happens to the 0.03%? My bad. What happens to the 0.3%? Because 100 minus 99.7 is basically 0.3. What happens to this 0.3%, which is usually beyond this line and beyond this line? Now this 0.3 percentage of the data is called as outliers. People also call it as anomalies. These are outliers. So if your data is following normal distribution, it is very easy for us to understand the outliers in the data. Now, how do you treat your outliers is a different story. But this is all about the empirical rule. There are different jargons, different words that we use. Mu plus minus 1 standard deviation is also called as 1 sigma. Mu plus minus 2 is also called as 2 sigma. Mu plus minus 3 is also called as 3 sigma. So sometimes when you hear what is 3 sigma rule, or what is empirical rule, or what is the normal distribution rule, do not panic. All are same. Normal distribution or Gaussian distribution. bell-shaped probability distribution. Most of the numbers are mid-range with less extreme values. Example 1, most people get mediocre score while small number of people get low score or high score, which is quite obvious. Whenever we have examination in our school days, majority of the people, I'm not it depends from exam to exam, from chemistry to English to mathematics, but the general idea is that majority of the people lies between this range. The range could be like 50 to 70, we don't know, and this could be the low marks and this could be your high marks. So another example is most people have an average height, but small number of people are extremely tall or short. Normally distributed data follows the 1 to 3 rule. Again, one more keyword. As I told you, 3 sigma rule or empirical rule or 1 to 3 rule, all are same. This rule states that there is a 68% probability, which is this one, 68.2 very precisely, almost 95% within this range, and 99 within your plus minus 3 standard deviation, 99.7 to be very precise. They lie between your 3 standard deviation of the mean. Now if you want to take some examples and try to solve this, probably you can do that. For example, let's say I have 10 students. I will write it down. Students marks, let's say mathematics marks. One of them has got 40, one of them has got 60, 65, 70, 75, 80, and one of them has got 72, 74, 70, 68, 92, 89, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 records. Sorry, 12 records. Now based on these 12 records, we'll try to calculate the mean standard deviation and see how many data points are falling within plus minus 1, 2 and 3 standard deviation. Obviously, like, to get the exact amount of 68 values, at least you need 100 records, right? Now if you take 10 records, either 6 or 7 records would be falling in this range logically, if the data is normally distributed. It cannot be 6.8, right? There cannot be 6.8 people falling under that category. So in order to have a concrete value, either you take a larger sample, or if you're taking a smaller sample, just adjust with the decimal places, right? Something like that. Now let's try to calculate the mean here. What will be the mean here? We'll try to calculate 40 plus 60, 100, plus 65 plus 70 plus 75 plus 80 plus 72 plus 74 plus 70 plus 68 plus 92 plus 89, which is 855. 855 divided by 12, which makes it 71.25. Similarly, standard deviation. Again, what I will do is I'll try to take help of one of the online tools, uh, or you can simply take help of your formulas. Standard deviation is nothing but summation of square root of xi minus mean square by n. Okay, let's try to take the traditional approach. So what I'll do is I'll probably create a we'll try to create a new page. So I have created a new page. Here, let me write down all the data points that I have. Now I realize that I should have taken a simpler example. Let's say 40, 60, 65, 70, 75, 80, 72, 4, 0, 6, 8, 72, 74, 0, 6, 8, 92, 89. 92 and 89. So what will be x minus mu? Imagine we are kind of rounding off the mu value. Let's say we'll consider 71. Okay, we'll round off the marks. The mu is 71. So what will be x minus mu? Minus 31, minus 11, minus 6, minus 1, 4, 9, 1, 3, minus 1, minus 3, 21, 18. I could be wrong, but I'm pretty much sure I'm not wrong. So x minus mu square, 31 multiplied with 31. It is 961, 121, 36, 1, 16, 81, 1, 9, 1, 9, 441 and 324. 21 into 21 is 441. Correct. Now what I will do is I'll try to add these numbers, because what we are doing is summation of xi minus mu square divided by n and then root over. This is what we are trying to do. So what is the numerator part? This part, the summation of all these things. So if I start calculating, 961 plus 121 plus 36 plus 1 plus 16 plus 81 plus 1 plus 9 plus 1 plus 9 plus 441 plus 324, 2001. Wow, great number. 2001 divided by 12, root over, divided by 12, which is 166.75 root over, which comes around 12.9. Again, we'll round off, make it 13. Now my mu is 71. My standard deviation is 13. Let's try to draw it. And right now itself, we will try to come to a conclusion whether our data is normally distributed or not. So the mean value is 71. Plus 1 standard deviation is 84. Plus 2 standard deviation is 97. Plus 3 standard deviation is 3910. Minus 1 standard deviation is 58. Minus 2 standard deviation is 45. Minus 3 standard deviation is 32. Right? Now, how many data points are lying between the first and the, like, in this range? How many data points are lying? 40 is not lying. This is lying, 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 lying. That's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 records. How many are within this range? Within 45 to 97, this. We have 11 records. And within this range, we have 12 records. So how much percentage do we have here? So if you calculate the percentage, 9 divided by 12, around 75%. Around here, we have 11 divided by 12, which is 91.6%. And around here, we already have 100%, which means there is no outlier in this particular data. It is somehow following normal distribution, but with no outliers. What if we had outlier? Maybe somebody, okay, somebody's score cannot go beyond 100 marks, but let's say somebody's score is less than 32. Maybe somebody is 16. Again, all these calculations will change here, right? The standard deviation calculations will change. So all these numbers will also change. You can do this activity, but this is how things work. This is how we usually do our normal distribution. Now, one question in our mind could be, do we deal with, I'll try to change the question, the data that we analyze on a daily basis as a data analyst, do we really care about normal distribution? is our data actually normally distributed? No, the answer is going to be no. Normal distribution is a very hypothetical scenario which rarely exists. Now, if it rarely exists, why do we even are learning about this concept? Because this is a very hypothetical concept. It is an ideal scenario. If the data is normally distributed, then it creates a lot of it gives you a lot of uh, opportunity to understand the data and do the analysis properly. A lot of data, almost 99.99% of the real time data, are never normally distributed. What if you get data which is not normally distributed, which is not like this, which could be like this, or which could be like this, or which could be like this? Now, this is not normal distribution. What will you do with this? Now, these are some scenarios which is called as skewness. There are some scenarios like skewness, scenarios like kurtosis, which is quite normal in any kind of data. If you encounter these kind of scenarios, either you convert the data to normal distribution or you deal with it, right? So in our next classes, we'll also talk about some concepts like skewness and kurtosis, and then I will also talk about some of the transformation techniques that we usually use to transform those kind of data that are overly skewed, highly or lowly skewed, like positively or negatively skewed, and try to convert the skewness data to a normally distributed data. That's all about this particular topic on normal distribution. I hope your concepts are clear. In the next video we shall talk about skewness and kurtosis. See you in the next video. Bye bye. Hi, welcome to this module on statistics, and in this video we shall be talking about skewness. In the last video you understood about the normal distribution, which is the Gaussian distribution and is also called as the Bell's curve. We understood that in a normal distribution, mean is usually the midpoint of the values of the records, and then we have mean plus minus 1 standard deviation, plus minus 2 standard deviation, plus minus 3 standard deviation. We also learned about the empirical rule, which basically says that 68% of the data falls between the first 1 plus minus 1 standard deviation, almost 95.4% of the records within the plus minus 2 standard deviation, and 99.7% data in the plus minus 3 standard deviation. What happens to the 0.3% data which is beyond this are basically called as the outliers. Now this is one of the generic scenarios. This is a very hypothetical scenario that we usually come across when we get started with the data analysis activities, when we start analyzing certain features, certain columns in a real day-to-day activity. We usually don't find any kind of data to be normally distributed. Now, there are so many problems with the data. Now, when we talk about problems, and that is where we are talking about skewness. What is skewness? Skewness measures the distribution of the data. It indicates whether the data is distributed symmetrically or not. If it is symmetric, then it is normally distributed. This is symmetric data. Data is evenly distributed on the left side, evenly distributed on the right side. If the data is not evenly distributed, then the different types of skewness are positive skewness and negative skewness. Now, look at this graph. Here, the data is not uniformly distributed. Not uniformly, sorry. Not, I would say, not symmetrically distributed, right? You can see there is a hump on the left hand side. Here, there is a hump on the right hand side. Normally, in normal distribution, your mean, median, and mode is your central line. But in this case, in the right skewed, you can see mode is here, median is here, and mean is here. So this type of scenario is called as right skewed. And when you see this kind of scenario, then it is called as a left skewed. These are the two different types of skewness. Now, the question that might be coming to your mind is, let's say we started analyzing data and we got that our data is right skewed or left skewed. How to fix that problem, or how to convert it into normal distribution? Well, there are a lot of transformation techniques. So some of the transformation techniques includes logarithmic transformation, square root transformation, cube root transformation. In case of some other scenarios, we might go for the square transformation. That means converting the data into the square format. Cube transformation, reciprocal transformation. So there are so many techniques that we usually do with the data, and then check their skewness score, whether their skewness score is within the range of 0 or not, like nearby 0 or not. In that case, we can assume that it is somehow in a better shape, somehow closer to the normal distribution. Well, the only problem now is all these kind of transformation techniques will need you to understand about pandas and numpy as well, which is going to be covered in one of the next modules. So what we will do is we'll try to take a pause here, try to understand this way. If your data has skewness, then it has to be transformed. How to transform using Python, pandas and numpy, we'll try to explain that in some of our future videos, in that either in that module or probably when we jump into the EDA sessions. In that class probably we'll talk about these things. That's all about skewness. In the next video we shall be talking about kurtosis. See you. Hi, welcome to this module on statistics, and in this video we shall be talking about kurtosis. Like the way we discussed about skewness in the last video, kurtosis simply means it measures the thickness of the distribution of data. The degree of tailedness of the data is measured by kurtosis. Kurtosis usually tells us the extent to which the distribution is more or less prone than the normal distribution. What are the different types of kurtosis? The normal distribution is basically called as meso. It is basically called as mesokurtic. Platykurtic is the red graph that you are seeing. It looks like a normal distribution, but you can see that it is somehow fat in this portion, right? Like larger number of data points are around here. Same with green, also following a similar pattern like normal distribution. The data is symmetrically distributed. The number of records here is very similar to the number of records here, but you can see that in this area less number of records are available. So kurtosis and skewness are completely different concepts. Skewness is all about the symmetric nature, but kurtosis maintains the symmetric ability. It is symmetric in nature, but you can see the issues. Issue is with the distribution of data. Now, if we identify these kind of scenarios, if we identify that we have a leptokurtic distribution or a platykurtic distribution, in that case also we go for the similar kind of transformation that we learned in the previous class. The transformations include log transformation, reciprocal transformation, square root transformation, cube root transformation, and so on. So that's a basic understanding on kurtosis. That's all about kurtosis. Probably once we learn about the pandas, numpy and the Python part, we will definitely come back to this topic and try to help you out on how practically we can solve these problems, how to solve the skewness problems and how to solve the kurtosis problems using Python code. That's all about this particular video. See you in the next video. Bye bye. Hi, welcome to this module on statistics. In this video, we shall be calculating probability with z-score for normal distribution. But before getting into z-score, let's try to understand what exactly is normal distribution and what is standard normal distribution. Normal distribution is somehow understood from some of our previous videos. You can see the left screen is basically the normal distribution, and this is how a data is distributed normally. Normal distribution, which is also called as Gaussian distribution, or which looks like a bell curve. You can see the middle point of this graph is your mu, which is nothing but your mean value. Similarly, you have your mu plus minus 1 standard deviation, mu plus minus 2 standard deviation, and mu plus minus 3 standard deviation. And we all know that within the first standard deviation, which is mu plus minus 1 standard deviation, almost 68% of the data lies. Between 2 standard deviation, almost 95.4%, and within 3 standard deviation, almost 99.7% data lies. What happens to the 0.03%, which is beyond this graph? Those are basically your outliers. And this is the scenario when it comes to normal distribution, which is a hypothetical scenario. Not all type of data will have a distribution like this, but the data that is following normal distribution, they will only be having distribution like this. Now, normal distribution is understood. What exactly is standard normal distribution? Before talking about standard normal distribution, let me talk about a concept called as feature scaling. Feature scaling. Feature scaling is a very important aspect in the field of predictive analytics, in short, in the field of analytics and data science. Now just imagine you have a height and you have weight. Let's just talk about height and weight. Simple. Let's say some of the customers' data that I have is, let's say, my bad. Some of them as having 170, 170, 160, 180. These are the different heights of people: 70 kg, 75 kg, 65 kg, and 80 kg. Now you can see both these height and weight are in different scale. One is in a hundreds format and one is in a tens format. Now what we do is we perform feature scaling on these raw data. The reason of feature scaling is we usually perform feature scaling so that all the variables, all the features like height, weight, and all the features that you are analyzing from a particular set of data comes into a certain scale. Now, why do we need to scale down the values? Because ultimately your data will be passed to a predictive model, to a predictive analytics model, which is otherwise called as a machine learning model. And in that particular model, you have to scale down the values. You have to get it in the scale of 0 to 1 or probably -1 to 1, which is a more readable format by the computers, because ultimately you're passing the data to a computer program, right? So feature scaling is an important aspect, and when it comes to feature scaling, two of the most important techniques is standardization and the second one is normalization. Now, when it comes to standardization, standardization is simply nothing but the new data is going to be x minus mu divided by sigma. And normalization, the new data is going to be x minus x minimum divided by x maximum minus x minimum. Now, in this case, we are applying the standardization technique to kind of do the feature scaling on the raw data. Now, we'll try to use this example, use this formula for standardization, which is z equals to x minus mu by sigma. Mu being the mean and sigma being the standard deviation. Let's try to calculate few things. We will try to calculate the z value where mu equals to mu, x equals to mu in this particular case. Now in this case, my z value will be x minus mu by sigma, which is x is going to be mu. So mu minus mu by sigma, which is going to be 0. And that is the reason the z value is 0 here. What will be the z value here? Mu plus 2 sigma. Z value is going to be x minus mu by sigma. I will replace x with mu plus 2 sigma. So mu plus 2 sigma minus mu divided by sigma. Mu cancel. 2 sigma by sigma is going to be 2. So the z value is 2. So as per this particular values, when you are converting into the standardization format or creating the standard normal distribution, the new points in your x-axis is going to be 0, 1, 2, 3, minus 1, minus 2 and minus 3, and these are called as your z-scores. The formula of which is already discussed, which is x minus mu divided by sigma. So if you want to find the probability, first step is to find out how far the value of x is from mu in terms of number of standard deviation. The number is named as z-score or standard score or z value. Basically, it tells you how many standard deviations away from the mean your random variable is. I hope everybody is clear with this thing. Let's try to also calculate the z-score at here and here. The z-score at here will be z equals to x minus mu by sigma. X is mu minus 3 sigma. So mu minus 3 sigma minus mu by sigma. Mu cancel. Minus 3 sigma by sigma. Sigma cancel. It's going to be minus 3. And that is the reason the value here is minus 3. So what only changes from this to this is the z-score. That's it. That means this is the standardized format or this is the feature scaled format. The values has been scaled down and the values that you see on the x-axis are your new values instead of mu plus sigma, mu minus sigma, and these values are called as z-score. The distribution in z-score, the distribution in standard normal distribution remains the same. It is still 68%, it is still 95%, and it is still 99.7%. That means if somebody asks you what is the percentage of data falls between a z value of plus and minus 1, then it remains the same. It's going to be 68%, which is the same here. Mu plus minus 1 standard deviation. That's all about this particular video. In the next video, we shall be talking about the examples of this particular topic. Hi, in this video, we shall be focusing on Z table. On your screen, what's visible is basically called as a Z-score calculation table or simply a Z table. On the left hand side, you will probably see various Z values ranging from negative values from minus 0 to minus 1.99. This basically refers to minus 1.99. Similarly, this table is all for the positive Z values starting from 0.00 to 1.99. Now, let's try to take an example and see how to use this particular table. So one of the examples is, just imagine there are 200 participants or applicants who have taken a statistics test. 200 people that have taken statistics test. Mr. John has basically got 700 score out of 1000. Simple. The average score was 600. So my mu value is going to be 600. And the standard deviation was 150. So sigma is 150. Now we would like to know how well John performed compared to his peers. So we need to standardize his score. That is, calculate a z-score corresponding to his actual test score and use a z table, which is this table, to determine how well he did on the test related to his peers as compared to his peers. In order to derive the z-score based on the information that we have, we will be using the formula z equals to x minus mu by sigma, which is nothing but My x is nothing but the score that John has got, which is 700, minus mu, which is 600, divided by 150, which is 100 by 150, which is almost 2 by 3, which is 0.666666. If you round it off, it will become 0.67. Now, for z value 0.67. Now, in order to figure out how well John performed on the test, we need to determine the percentage of his peers who go higher and lower scores. That's where your Z table comes into picture. If you noticed, there are two Z tables, one with the negative values and one with the positive values. If a Z score calculation yields a negative standardized score, refer to the first table, otherwise refer to the second table. As the Z score is positive, so the left table is out of scope. We will be focusing on the right table. So what we will do is we will try to see 0.67. So 0.6 is here, 0.60, 0.61, 0.62, 0.63, 0.64, 65, 66, 67. So at 0.67, my value is 0.7486, which is basically nothing but 74.86%. This means that almost 75% of the students scored lower than John, and only around 25% of the students have scored more than John. So if I talk about the real percentage, as we have 200 students, the final outcome or summary is basically that 75% student out of 200, 75% of 200 is basically 150. That means John did better than 150 students. And that is how you see your Z score table. I hope that was informative. In the next video, we shall be taking another example and see how to solve this particular problem related to Z score. See you in the next video. Bye-bye. Hi. Let's take another example related to this topic. We will be taking an example of height distribution in a class. Imagine you are doing a study on the height of a class of university students. Assuming that the height is following a normal distribution. Let's say the height is following normal distribution. What is the percentage of students who are shorter than 1.5 meters? That's fine. Let's say we'll try to draw this again. Imagine the data is following normal distribution. Looks something like this. What percentage of students are shorter than 1.5? The average height of the class is 1.6. So let me just draw it. 1.6. Standard deviation is 0.06. So plus 1 standard deviation will be 1.66. 2 standard deviation will be 1.72. 3 will be 1.78. Minus 1 standard deviation will be 1.54. 2 will be 1.48. 3 will be 1.42. That means this is basically your plus minus 3 standard deviation, which should have 99.7% data. This is plus minus 1 standard deviation. This is plus minus 2 standard deviation. Now talking about this question, what percent of the students are shorter than 1.5 mm? Where does 1.5 mm falls? 1.5 mm is somewhere here. That means I need to find how much percentage is beyond this particular line, right? Everybody is clear? So the first thing that we were going to perform is calculating the Z score. So again, we will take the help of the formula Z equals to x minus mu by sigma. At 1.5, we are going to calculate the Z score. So 1.5 minus 1.6 divided by 0.6, which is 0.1 minus 0.1 divided by 0.6, which is going to be 1.5 minus 1.6 divided by 0.06, which is minus 1.67. Minus 1.67. Clear? So the z-score at 1.5 meters is minus 1.67. Now look up the probability form, the z-score table. You can see minus 1.67. 0, 1, 2, 3, 4, 5, 6, 7. So this is the value. If I take this value, it is, sorry, my bad, it is 0.0475. If you multiply it with 100, that becomes 4.75%. That means 4.75% of the people, of the students, are shorter than the range of 1.5 meters. And that is how you use your Z table or your Z score table to identify such kind of problem solutions. That's all about this particular video. In the next video, we shall be talking about various other things. See you in the next video. Bye-bye. Hi, welcome to this module on statistics, and in this video we shall be talking about covariance and correlation. This is how the agenda looks like. In this series we are going to talk about covariance, and then we will talk about correlation, and then we will talk about how covariance and correlation are related to each other. Is there a relation between covariance and correlation? If yes, what is the relationship? Stay tuned. We'll see you in the next video. Bye. Hi, welcome to this module on statistics, and in this video we shall be talking about covariance. What exactly is covariance? Covariance is simply a statistical term that refers to a relationship between two random variables on how one variable changes would impact the other one. In simple terms, if you are analyzing two features or two variables, let's say height of a customer and weight of a customer. This could be your height, this could be your weight. Now obviously when you start plotting the points, this is how the points looks like. In this case, it's quite evident that when the height is increasing, the weight is also increasing, right? So covariance basically helps you to find the relationship between two random variables. Covariance values can range from minus infinity to infinity. Positive covariance denotes a direct relationship and is represented by a positive number. So if you find the covariance between two particular parameters or two particular variables is positive, then you can say that it is positive covariance. If one variable is larger, then other one is also larger. If one variable increases, the other increases. If one variable decreases, the other variable decreases. Similarly, a negative covariance indicates an inverse relationship between the two variables. If one variable is larger, then the other is smaller, and vice versa. The value does not represent the magnitude of a relationship, only the direction matters. So, as I said, the values could range between minus infinity to infinity. And from this point, it is clear that the magnitudes are not that important. What's important is that if the covariance value is positive or negative. If it is positive, then simply there is a positive correlation or positive covariance between two variables. I talked about a term called correlation by mistake, but we will be talking about correlation in our next slides. So let's just focus on covariance. Okay. So when it is positive, then means it's a positively covariance between two variables. And if it is negative, then negatively covariance. Now just imagine you are dealing with four features, x1, x2, x3, x4. The covariance between them is 5. The covariance between them is 10. Can we say that this is a stronger relationship? It's not that. it's not the case. As I told you, that magnitude does not matter. Whether x1 and x2 is a stronger relationship or x3 and x4 is a stronger relationship, that is possible to find out using another concept called as correlation, which we will study. But covariance only tells us whether they are positively covariated or negatively covariance. We'll try to go ahead to the next slide where we will talk about the formula. Covariance formula looks pretty complicated, but it is very simple. Now the formula here is 1 by n summation of I equals to 1 to n xi minus x bar multiplied with yi minus y bar. So this basically is yi. Now xi is nothing but your first variable. Yi is nothing but your second variable. X bar is nothing but the mean of x. Similarly, y bar is nothing but the mean of y. This is a summation symbol. That means if you have 5 numbers, 5, 10 and 15, the summation of this will be a combination of all. 5 plus 10 plus 15, right? And we have 1 by n. Again, this formula changes from population to sample. I hope you remember about population data and sample data. In case of population, it has to be 1 by n. In case of sample data, it has to be 1 minus n minus 1. Okay, so we have mentioned here 1 by n, assuming that we are talking about population. But in case we go ahead and solve a problem using a sample data, then our formula will change. Right? Now, going ahead and talking about an example. So this is an example, stock market movement of two relevant stocks in the same industry. So we have 5 days of data. It is quite obvious that it's a sample data. In that case, our formula becomes covariance of x comma y becomes 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. Okay. Now, let's try to draw a small table. So we have day, stock 1 and stock 2. So this stock 1 is nothing but my x and this is nothing but my y. These are my two variables, two stocks. And between these two stocks, our main aim is to identify the covariance, whether it is positively covariance or negatively covariance. So I'll try to rub everything off from the screen. So here I'm going to mention x. Here I'm going to mention y. So x is 3%, 2%, 6%, 1% and 0. Y is 5%, 4.5, 9, 1 and 1. So writing down the formula again, my mistake of rubbing it off, 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. So first thing is I have to find x minus x bar and y minus y bar. Before that, let's try to find what is x bar and what is y bar. X bar is nothing but the mean of x. Simple. The mean of x here is going to be 3 plus 2 plus 6 plus 1 divided by 5, which is 3 plus 2 5 plus 1 6 plus 6 12 by 5, which should be 2.4. 5 plus 4.5 plus 9 plus 1 plus 1 by 5. 5 plus 4.5 9.5, 18.5, 20.5. 20.5 divided by 5 should be 4.1. So this is my 2.4 and 4.1. Cool. Now we have to find x minus x bar. So for the first record, what will be x minus x bar? It will be 3 minus 2.4, which is 0.6. 2 minus 2.4, which is minus 0.4. 6 minus 2.4, which is 3.6. 1 minus 2.4, which is minus 1.4. 0 minus 2.4, which is minus 2.4. Clear? Similarly, we will do it for y minus y minus y bar. 5 minus 4.1, 0.9. 4.5 minus 4.1, 0.4. 9 minus 4.1, 4.9. 1 minus 4.1 minus 3.1 and minus 3.1. Clear? Now what we will do is we will add it, like we will do the product of this one and this column. Of this column and this column, we will do the product. That means we will multiply them. So 0.6 multiplied with 0.9 is 0.54. 0.4 minus 0.16. 3.6 multiplied with 4.9. 36 multiplied with 49. 36, 40, 720, 1440. 17.64 is what I guess. 3.6 multiplied with 4.9. Yeah, 17.64. 17.64. 1.4 multiplied with 3.1. So 14 multiplied with 31. Okay, you can use the calculator for this one. It should be 4.34. And negative, negative, positive. Okay, the multiplication of two negative numbers is always positive. Similarly for this one, 2.4 into 31, 24, 30, 48, 72, 720, 744, 7.44. Okay, that's my 5 numbers, right? So this is being calculated. Now what is this parameter? That means sum of all these numbers. So we'll sum it up. The sum of all these numbers is 0.54 minus 0.16 plus 17.64 plus 4.34 plus 7.44 divided by 5. Now we'll not divide it by 5 right now. Let's just calculate the whole sum. Okay, we'll take the help of calculator. The whole sum is coming up to 29.8. Okay, now we will try to use the covariance formula. Covariance of xy is equals to 1 by, this is a sample data, so we'll consider n minus 1, summation of x minus x bar multiplied with y minus y bar. 1 by n minus 1 multiplied with this thing. This entire thing is 29.8. Now this becomes 29.8 divided by 4, which becomes 29.8 divided by 4, which becomes 7.45. And this is your covariance between stock 1 and stock 2. Looks like a positive number, so it's a positive covariance. That's all about this particular topic on covariance. I hope you understood the basic concept behind covariance and you understood how to solve a problem and how to find the covariance given to features. If you have more features, then you can simply calculate in the same fashion. But honestly speaking, when we jump into the future topics related to Python, pandas and all those things, you can simply find covariance and various other statistical concepts using just one line of code. So do not worry, that is how the programming languages help you. Now that's all about this particular topic on covariance. In the next video we shall be talking about correlation, and then lastly we will be talking about the difference between covariance and correlation, which one to use, which one not to use, and all those things. That's it. See you in the next video. Bye bye. Hi, welcome to the module on statistics, and in this video we shall be talking about correlation. What exactly is correlation? Correlation is similar to covariance. We studied about covariance in the previous session, in the previous video. Correlation is similar to covariance also for measuring how two variables are related or moving together. When two sets of data are strongly linked together, we say they have a high correlation. The word correlation is nothing but a combination of co and relation. Co means together and relation is relation. Correlation is normally positive when the values increase together, and is negative when the values decrease together, as in one increases and the other decreases, right? A correlation is assumed to be linear following a line. Now, correlation is always ranging between +1 to -1, which means if I draw a graph like this, imagine you are analyzing height and weight. Now, this is a clear case of very high correlation where your correlation value will somewhere be near to 1. And in this case, as height increases, your weight also increases. Another case of correlation is something like this. You have height and weight. Imagine you have data like this. Somehow the data is scattered within this range, but you can see the positive correlation. You can see that they are moving towards the same direction. When the weight is increasing, the height is increasing as well. This is also a case of positive correlation, but it could be a low positive correlation. I'm not exactly sure about the exact value, but should be somewhere around 0.5 to 0.8 or something like that. Imagine a case where you are analyzing two features, height and weight, and the points are something like this, which is clear. When the height is increasing over the x-axis, the weight is decreasing. You can see a negative correlation here. Here, the correlation value will be somewhere near to minus 1. Could be like minus 0.5 or minus 0.3 or something like that. Whenever you see a graph like this, let's say height and weight, and the data points are randomly distributed, so nobody can sense whether there is an increasing trend or a decreasing trend. It's very difficult to interpret. In these kind of scenarios, we call it as no correlation or zero correlation. And normally in these cases, the correlation value is somewhere around 0. Exact numbers again are not known. Mathematically, there are ways to find the exact number, but visually it's not difficult. It's very difficult to interpret the exact value. But try to understand this thing, that correlation and covariance are almost similar to each other, but the only difference is covariance ranges from minus infinity to infinity, but correlation ranges from -1 to 1. And another big difference is that in correlation, both direction and magnitude are useful. That means if you are analyzing two features x1, x2, x3, x4, the correlation between x1 and x2 is 0.9, the correlation between x3 and x4 is 0.5. It clearly means that this is a stronger, it's not, my bad, it's not greater than equal to with the flow I just wrote, but it's quite evident that this relation is stronger than this, which is not the case in covariance. Your covariance value could be like 7, it could be 5, then you cannot clearly say whether this is a stronger relationship or not. That is the only difference between correlation and covariance. But which one to use, which one to not use in real life scenarios is something that is debatable. We'll be covering that in some of our future videos, but let's go ahead and watch out the correlation functions formula. Pearson's correlation coefficient P of xy is basically called as correlation of xy. The formula is very simple. It is covariance divided by standard deviation of x multiplied with standard deviation of y. In simple terms, this is nothing but covariance of xy divided by standard deviation of x multiplied with standard deviation of y. So here it is mentioned as variance of x and variance of y, and we all know that standard deviation is nothing but variance square, right? So variance is nothing but your sorry, my bad. Standard deviation nothing but root over of variance. My bad, my bad. Right? So this is your standard deviation x and standard deviation y. Now we'll try to take this formula and try to solve the same problem which we were trying to solve in the covariance thing. In the covariance chapter, if you remember, then the covariance was calculated as 7.45. I still remember this. Let me write down the covariance formula as well. Covariance of xy was nothing but 1 by n minus 1 summation of x minus x bar multiplied with y minus y bar. I still remember this part was 29.8 and again divided by 4, which was 7.45. Right. Now we'll try to solve correlation. In order to solve correlation, we have to find the sigma of x and sigma of y. What is the formula of sigma? We all remember it's summation of xi minus mu square divided by n minus 1 root over. So again we'll write it down, x, y, 3, 2, 6, 1, 0, 5, 4.5, 9, 1, 1. What was x bar? X bar was 2.4 and y bar was 4.1. So what is x minus x bar? 3 minus this, which is 0.6. I'm just repeating all these things. This was already calculated. 3.6 and minus 1.4 and minus 2.4. Y minus y bar was 0.9, 0.4, 4.9, 3 minus 3.1 minus 3.1. Let me just rewrite it. Minus 3.1. Done. So we will calculate the numerator part, which is x minus x bar square. And again we will do the same for y minus y bar square. What is x minus x bar square? 0.36, 0.16, 3.6 into 3.6. It is 12.96. 1.4 into 1.4 is 1.96. 2.4 into 2.4 is 5.76. Similarly, this one will be 0.81, 0.16, 4.9 into 4.9 is 24.01. This is 3.1 into 3.1, 9.61 and 9.61. So we'll try to calculate this. So summation of this is nothing but 0.36 plus 0.16 plus 12.96 plus 1.96 plus 5.76 is 21.2. What is the summation of this? 0.81 plus 0.16 plus 24.01 plus 9.61 plus 9.61, which is 44.2. So what will be sigma of x, the standard deviation of this? We know the numerator, 21.2 divided by 4 root over, which is somewhere around 2.3. Sigma of y will be 44.2 divided by 4 root over. 44.2 divided by 4 is around 11.05 root over 3.3. Done. Y4, because this is sample data, right? Now coming back to Pearson's coefficient, which is covariance divided by standard deviation of x multiplied with standard deviation of y, which is 7.45 divided by 2.3 multiplied with 3.3. So what is the value? If I calculate 7.45 divided by 2.3, which is 3.23, divided by 3.3, which is 0.98, which clearly means that they are heavily correlated or largely positively correlated. Now let's try to draw the graph. Let's say x1, which is my stock 1, and the y, which was my stock 2. So let's say 1, 2, 3, 4, 5, 6, and let's say here 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And this is 1, 2, 3, 4, 5, 6. So the first one is 3, 5, which is 3, 5 somewhere here. 2, 4.5. 2, 4.5 somewhere here. 6, 9. 6, 9 somewhere here. 1, 1. 1, 1 somewhere here. And 0, 1. 0, 0, 1 somewhere here. So this is how my different points looks like. Obviously, it is quite clear that they are positively correlated. That means when my stock 1 goes high, my stock 2 also goes high. Now you know whether when you are analyzing the stock market, if there is a positive correlation or a positive covariance, at least when it comes to correlation, if the correlation is something like this, and if you're investing in stock 1 which goes up, you know which stock to play around. Well, pun intended, I was just joking. So that's all about covariance example, but we were trying to solve the correlation part. So the wording here is a little bit different. The wording here is covariance example because we were taking the same example, but we kind of use this same example to calculate the Pearson's correlation, right? So in this case, for stock 1 and stock 2, the Pearson's correlation comes around as 0.98. Talking about the interpretation of correlation, we all know correlation values ranges from -1 to 1. So when you are analyzing data, your values could range somewhere between that. Let's just talk about the positive case scenarios where I'm talking about 0 to 1. When you have a number like this within a range of 0.7 to 1, then we say that strong linear relationship. When there is a value within the range of 0.3 to 0.7, moderate linear relationship, and 0 to 0.3 is a weak linear relationship. That means weakly positively correlated. And similarly the other way around, right? Minus 0.3 to 0 could be a weak negative. Minus 0.3 to minus 0.7 again could be a moderate negative relation. Minus 0.7 to 1, sorry, minus 1 could be a strong negative correlation. In these kind of scenarios, you could assume the data points would be something like this. When one increases, the other decreases. Applications of correlation. There are humongous applications of correlation. To be very honest, correlation is one of the strong statistical concepts that we use in exploration of data. While analyzing data, while doing the data analysis, correlation plays a very vital role. Obviously, you will be taught about EDA and all those concepts. So here, one question is explore what are the variables that are correlated among a large number of variables. You have 100 variables about a person. Which one is related to their online purchase habit? So in that case, what you can do is number of online purchases. That's your variable 1, and one by one you can analyze the Pearson's correlation between age and this. For gender also, you can probably convert it into numerical values and then find the correlation, or average daily time, monthly income. So all this can be done. With the help of Python, it will take you hardly 1 or 2 lines of code to understand the correlation. And of course, using various correlation, You can also plot some beautiful heat map diagrams to understand everything. So all these concepts will be taught slowly. That's all about this particular session on correlation and covariance. That's it. See you in the next video. Bye bye. Hi, welcome to this video on statistics. In this video, we shall be doing a small debate around the difference between covariance and correlation. However, we understood each and every concept. We know what is covariance, we know what is correlation mathematically and non-mathematically. In this video, we will be doing a small difference between each one of them and we'll try to see the difference. Covariance and correlation. The meaning is almost similar to both. Both of them measures how two variables are moving or related to each other. If you see a positive covariance, then your A and B are moving in the same direction. If you see a positive correlation, A and B are moving in the same direction. If you see a negative number, A and B are not in the same direction. If A increases, B decreases, and vice versa. Same goes with correlation also. So definition wise and the meaning wise, both are similar. I would not say same, both are similar. Value wise, of course, covariance ranges from minus infinity to infinity. It could literally be any number: 7.5, minus 1.5, minus 9.1, 8.9, and so on. But correlation always lies between minus 1 to 1. If it is closer to minus 1, highly negatively correlated. If it is closer to plus 1, highly positively correlated. If it is near to 0, then no correlation. Direction. Direction wise also both are same. Positive or negative represents how two values or two variables are moving together. Magnitude wise is where the difference comes. Magnitude wise covariance is not useful. It does not indicate the magnitude of the relationship, which means if you are having four variables x1, x2, x3, x4, it could be anything: age, salary, tenure, something else. If x1 and x2 covariance is 5, x1 and x3 covariance is 7, x1 and x4 covariance is 3, that does not mean that these two are having a strong relationship as this. But in the case of correlation, if x1 and x2 are having 0.9, x1 and x3 are having 0.7, and x1 and x4 are having 0.3, it is quite clear that this is a stronger relationship than this, which is a stronger relationship than this. So the value represents how strong the relationship is. Can compare for a different group of variables based on the values. Example, whether AB have a strong relationship compared to AB. No. And this one will be yes. That's all about the difference between covariance and correlation. The more you jump into the practicals part, you will have more understanding on which concept to use, which one not to use. But most likely and majorly in the field of data analysis, when you're analyzing multiple parameters, multiple features, variables, correlation is something that is highly used. But from the terms point of view, just make sure you also understand what covariance is all about. That's all about this particular video, and this potentially comes to an end to this module. See you in the next video. Bye bye. Hi, welcome to this module on statistics, and in this video we shall be talking about hypothesis testing. What is hypothesis testing? Hypothesis testing is a statistical method that is used in making statistical decisions using experimental data. Hypothesis testing is basically an assumption that we make about the population parameter. I hope everybody knows about population and sample. So hypothesis testing is basically an assumption that we make about the population parameter. For an example, you say the average student in a class is 40 or a boy is taller than girl. All those examples we assume need some statistic way to prove. We need some mathematical conclusion, whatever we are assuming is true. What if somebody says you that the average height of people in Japan is 170 centimeters? How are you going to prove it? That's a hypothesis that you are building. So we need some mathematical conclusions. We need some conclusions that has to be statistically proven, and because of that only we are using hypothesis testing. Why do we use it? Hypothesis testing is an essential procedure in statistics. A hypothesis test evaluates two mutually exclusive statements about a population to determine which statement is best supported by the sample data. When we say that a finding is statistically significant, it's thanks to a hypothesis test. Which are the most important parameter of hypothesis testing? Well, the image that you see on the screen is something related to normal distribution. I hope everybody is clear with these concepts of normal distribution. This is basically a standardized normal distribution because the center line you see is 0 and then you see plus minus 1, plus minus 2, plus minus 3. Right? Anything lies that beyond plus minus 3 standard deviation or beyond plus minus 3 z score is basically your outlier. Anyways, getting back to the topic of hypothesis testing, there are majorly two types of hypothesis under hypothesis testing. The first concept is null hypothesis, and the second concept is alternate hypothesis. Let's try to understand each one of them. Now that we are talking about inferential statistics, in inferential statistics, the null hypothesis is a general statement or default position that there is no relationship between two measured phenomena or no association among groups. In other words, it is a basic assumption or made based on domain or problem knowledge. What if you say that the company's production is 50 units per day? That becomes your null hypothesis. So the company's production is 50 units per day. That means if the company's productions is proved that it is not 50 units per day, then you'll probably have to reject your null hypothesis, right? Talking about alternate hypothesis, obviously alternate hypothesis is the opposite of null hypothesis. The alternate hypothesis is the hypothesis used in hypothesis testing that is contrary to the null hypothesis. It is usually taken to be that the observations are the result of a real effect with some amount of chance variations superposed. Anyways, so alternate hypothesis example will be the opposite of null hypothesis, which in this case will be the company's production is simply not equals to 50 units per day, right? So there are some general fundamentals behind null hypothesis and alternate hypothesis. General assumptions, my bad. So what are those assumptions? The assumptions are null hypothesis can have equals to, greater than equals to, or less than equals to in their statement. So equals to, greater than equals to, or less than equals to. Alternate hypothesis should not have all those things. They should have not equals to, less than, or greater than. Try to remember this statement, which is very easy to remember. Now, talking about a case study or one simple statement that a company has made. Let's say Amazon claims that their revenue last year was at least $14 billion. At least 14 billion. That means either 14 billion or greater than that. So in that case, your null hypothesis will be Amazon's revenue last year was greater than equals to $14 billion. So the null hypothesis is the same and alternate hypothesis is the opposite of that. which is less than 14 billion. So your H0, which is nothing but your null hypothesis, is basically your revenue is greater than equals to 14 billion, and H of 1, which is your alternate hypothesis, is less than 14 billion. So this becomes your H1 and this becomes your H0. My bad. So there is a small change here. My bad. Right? So this is your H0 and this is your H1. Now what if similarly, let's say Amazon's revenue last year was at most $14 billion. That means either it was less than or equals to 14 billion. It was not beyond that, right? In that case, your symbols will change here, right? So, based on the statements, we can define our null hypothesis and alternate hypothesis. So that's all about the basics of null hypothesis and alternate hypothesis. In the next video, we shall be talking about some tailed tests. See you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about p-value and significance value. Now, what exactly is significance value? The term significance value or significance level, or called as alpha, is used to refer to a pre-chosen probability, and the term p-value is used to indicate a probability that you calculate after a given study. P-value, where the P symbolizes probability. The P-value or calculated probability is the probability of finding the observed or more extreme results when the null hypothesis 𝐓𝐢𝐻𝐢𝐦𝐞𝐋𝐢𝐧𝐞 of a study question is true. The definition of extreme depends on how the hypothesis is being tested. Let's try to take an example and try to understand more about the p-value. You have a coin and you don't know whether that is fair or tricky. So let's decide null and alternate hypothesis. The null hypothesis, which is 𝐻(0), is considered that a coin is a fair coin, and 𝐻(1) is that a coin is a tricky coin, and alpha equals to 5% or 0.05. So we have already defined our significance level as 0.05. Now let's toss the coin and calculate the p-value, which is the probability value. Toss a coin first time and the result is tail. So the p-value is 50%, as head and tail have equal probability, right? When you're tossing one coin, there are two outcomes. Either it is a tail or a head. So the p-value comes as 50%. Toss another time the second coin and the result is tail again. Now what is the p-value? The p-value is 25%, because getting two tails out of flipping two coins is 25%, because the four combinations are HH, HT, TH and TT. So getting a TT is 1 by 4, which is 25%. Similarly, the process goes on, third time, fourth time, fifth time. So toss 6 consecutive time and you got the p-value as around 1.5%. So second time when you are tossing, p-value is 25%. Third time, 12.5%. Fourth time, 6.25. Fifth time, 3.125. And sixth time, almost 1.5 times, 1.5%. Right? But we set our significance level as 95%, which means 5% of error rate is allowed. And here, as we see that we are beyond that level, that is, our null hypothesis does not hold good. So we need to reject and propose that the coin is a tricky coin, which is actually. And that is all about this p-value and significance value. Why do we set the significance value as 95%? This is what statisticians has already set. Significance level of 95% is a preset value that many statisticians have already set. So we usually consider 95% as our significance level, which means with 95% confidence, and 5% of error is allowed. That's all about the general concept behind p-value and significance level or significance value. In the next video, we shall be giving you a brief idea about the types of tests, and we will be showing you which type of test should be used in which type of data. See you in the next video. Hi, welcome to this module on statistics. In this video, we shall be talking about the next test, which is t-test. In the previous video, we talked about z-test. In this video, we are going to focus on the t-test. Before getting into t-test, let me try to talk about the data. In this particular example, I am going to take two types of data. There are 10 female customers and 10 male customers, and each one of them has their ages mentioned here. Now, we are going to perform two types of tests. For the first thing, what we need to do is we are just going to focus on only these 10 female customers. So we will try to test to determine whether the female population mean age is significantly greater than 30. That's going to be my case. Now, what is going to be my hypothesis? My null hypothesis is going to be mean is less than equals to 30, and my alternate hypothesis will be mean is greater than 30. So I'm only considering one sample. So we are doing a one sample t-test. Now, in order to accomplish this thing, let me just note down few other things as well. My significance level is as usual going to be 0.05. If my p is greater than 0.05, then we accept the null hypothesis, else we reject the null hypothesis. I think everybody is clear till here. Now, I'm going to only considering that this particular column, which is the first column, as we are doing one sample t-test. So what I will do here is I'll probably go ahead and click on data and go to data analysis. And here you can see there is an option called as t-test to sample assuming unequal variances. I'm going to do that, but before that I'm going to just create a dummy variable. Dummy variable is just created, it's just a dummy data because there is no option called as one sample t-test. So we are going to use two sample t-test, but we are going to use the second variable as this dummy variable. Once you click on OK, let me just empty all these records. Now this is how your original window looks like when you open the data analysis and open the t-test for the very first time. The first variable range will be this. The second variable being the dummy variable, the range will be this. I'm going to click on labels because my first selected data is the header. My hypothesized mean difference is going to be 30 because here the test is to determine whether the female population mean age is significantly greater than 30 or not, right? Now, output range, I will select this particular cell and click on OK. Now, once this is done, this is how my test looks like. I'll probably delete this cell because it contains my dummy data, and I will rename it to one sample test. That's it. And instead of hypothesized mean difference, I'll note it as hypothesized mean. Everything else remains the same as this is a one-tail test. Let me just get it back to this side. Okay, as this is the one tail test and my p value is 0.052, which is greater than 0.05. So in this case, I'm going to accept the null hypothesis. So I will note it down as green. I'm going to accept the null hypothesis because the p value is greater than 0.05, and this is a one tail test. Now we will perform another test which is going to be for both these particular features. Now if I am considering both these features, what will be my new H0 or null hypothesis? My new null hypothesis will be there is no significant difference between the mean age of male and female. The same hypothesis we also used in the Z test. There is a significant difference between the mean age of male and female. Okay, this is my new hypothesis. I'll note it down here maybe, or else here. Okay, let's note it down here itself. Okay, no problem. So this is my hypothesis. Okay, now I'm going to use both these samples. So again, I will click on data analysis, click on the same thing. Here, let me remove everything first. The first range is going to be my all the female customers age. The second range is going to be all the male customers range. And then the hypothesized mean difference is going to be 0 because I'm going to consider two samples, female and male. So my hypothesized mean difference is 0 because my assumption is there is no significant difference between the mean age of male and female. That means the mean age of male is equivalent to the mean age of female. The output range is, I'm selecting this cell. Done. Everything else looks fine. I'll click on OK. And this is my two sample test for this. Here my p value is also greater than 0.05. You can see the p value is 0.07, which means it is greater than 0.05, which means we are going to accept the null hypothesis. And what is the null hypothesis? The null hypothesis is there is no significant difference between the mean age of male and female. I hope you understood both these aspects of t-test, on how to perform t-test on a sample test, on one sample test, and how to perform t-test on two sample test. That's all about this particular video on t-test. In the next videos, we shall be talking about various other tests. See you in the next video. Bye-bye. Hi. Welcome to this module on statistics, and in this video we shall be talking about the two types of tests that we perform in hypothesis testing. So one of the tests is called as one-tailed test and the other test is called as two-tailed test. Now the difference between each one of them is super simple. One-tailed test, a test of a statistical hypothesis where the region of rejection is on only one side of the sampling distribution, is called as a one-tailed test. Now for example, a student has greater than equals to 800 marks, or math score is greater than equals to 80%. So what is the area of rejection? The area of rejection is simply the opposite of it, which is less than 800 marks or less than 80%, which is one side of your graph. And that is one of the reasons we call it as a one-tailed test. Similarly, a two-tailed test is a statistical test in which the critical area of a distribution is two-sided and tests whether a sample is greater than or less than a certain range of values. If the sample being tested falls into either of the critical areas, the alternate hypothesis is accepted instead of the null hypothesis. Now for an example, a student has the student's total marks is not equals to 800. Now there are two probabilities here. If they are not equals to 800, that means we accept the hypothesis, right? If it is not equals to 800, it could be less than 800 or it could be greater than 800. So there are two chances of having an of rejecting this statement. It could be less than 800, it could be greater than 800. So this is a two-tailed test, right? So that's all about the simple definition between one-tailed test and two-tailed tests. We basically consider these both tests while performing any kind of statistical tests in order to have an hypothesis testing. So once we jump into the practicals part, we'll be able to showcase and let you know in a better way. See you in the next video where we will be jumping into the difference between p-value and significance value. Hi, welcome to this module on statistics, and in this video we shall be talking about the types of test. As we all know, there are different types of tests, one being t-test, then we have the z-test, we also have ANOVA, we do have chi-square test, and finally we have the correlation test. We all know that these tests are the various statistical tests to kind of test our hypothesis. We usually start with a null hypothesis and an alternate hypothesis. We perform these tests to validate our hypothesis. Now, before getting into each of these tests, let's try to analyze and discuss about few scenarios. We already know data is majorly of two types, one being categorical data, which is your qualitative data, and one being your numerical data, which is your quantitative data. Again, talking further about qualitative data, there are two further types, which is nominal and ordinal. If you are new to these topics, definitely go back to some of our videos related to data and qualitative and quantitative data. You will get understanding on those kind of videos. Even we also discussed about various numerical types, which is discrete and continuous, right? We all discussed about these basic concepts. Now, getting started with this, imagine you want to analyze one categorical feature. Now, one categorical feature, let's take an example of gender. And you come across this situation where you know that there are two valid values in gender, which is F and M. F belongs to female and M belongs to male. Now, what is the best way of representing this data visually? The best way could be a bar graph, or it could be a pie chart as well, which can also tell you the distribution between F and M. But bar charts are highly recommended for categorical features. Similarly, talking about one numerical attribute, let's say we'll talk about age. Let's say you are analyzing age of multiple customers and somebody asks you, can you tell me the statistical information from this? Provide me all the statistical information. Try to do a memory refresher. Statistical information basically means understanding your Q1, Q3, your median value, your mean value, your maximum value, your minimum value, and so on. Right? Now, what is the best way of getting all this information? Probably by plotting a box plot. Similarly, if you want to make it more complicated, let's talk about two categorical features. Let's say gender and location. Again, what could be a better way of visualization? I would again pick bar graphs. Let's say we have two locations, Japan and India. So this is Japan and this is India, and this is how the distribution of female and male people are in different countries. Similarly, making things more complicated before going into the two numericals part, I'll talk about one categorical and one numerical. One example could be for categorical, let's take gender, and for numerical, let's take age or income. How do you want to visualize or analyze these kind of features? And in gender, we have F and M. How about for female, I draw a box plot, and for male customers, I also draw a separate box plot, and then I identify the statistical information from each one of them. Possible? Quite possible. Lastly, I'll talk about two numerical features. Now, let's say I'll talk about two numerical features. Okay, let's talk about two numerical features. We'll talk about two numerical features. Let's say age and salary. And let's say I plot something like this, where this is your age, this is your salary, and you plot some data points. So you can easily plot scatter plots to identify the relationship between age and salary. If it looks like this, probably the correlation between age and salary is high. If the graph looks like this, probably the correlation is low, or maybe you can call it as negatively correlated. If the data points are randomly distributed, there could be no correlation, right? That is all about the different types of data. Now, coming back to our topic, what we can do is, as there are multiple types of tests and multiple types of data, which test do we conduct for which type of data? So we'll try to draw a small graph, a small table. Let's say my first column is type, that says the type of data. The second, what we see. And the third one is the type of test. Talking about one categorical, and then one numerical, then one numerical plus one categorical, then we have two categorical, and then we have two numerical. What we see, when we analyze one categorical data, we see something like this. What we see in one numerical data, we see something like this, a box plot. In one categorical and numerical data, we see some box plots like this for multiple categories. For two categorical data, probably we see some bar graphs like this. And for two numerical, we see some scatter plots like this. So the type of test that we usually perform on one categorical data or one categorical feature is called as one sample test. Similarly, for one numerical data, t-test is recommended. T-test, Z-test, I will talk about the differences between these kind of tests in the next video, but t-tests and Z-test are almost similar. I'll talk about the differences in the next video. Similarly, when we talk about one numerical and one categorical, we talk about t-test, or you can also use ANOVA. Again, inside ANOVA, there are multiple subtypes of ANOVA, which is one-way ANOVA, two-way ANOVA, that we will again explore and see how ANOVA can be used. Talking about two categorical features, we usually go for chi-square test. And lastly, we go for correlation test. So this is an overall idea about which type of tests has to be used for which kind of data and how do we see the data. That's all about this particular video. I hope you enjoyed it. In the next video, we shall be jumping into each and every test and we'll try to implement that test using our dummy data in Excel. See you in the next video. Bye-bye. Hi, welcome to this module on statistics, and in this video we shall be talking about our first statistical test, which is Z-test. In the previous video, we talked about the general overview about the different types of statistical tests, and we also discussed which type of test is applicable for which type of data. For one categorical data, one numerical data, combination of numerical and categorical, two categorical and two numerical. there are different types of tests that we perform. The first test that we are going to see today is going to be on Z test. In order to perform this Z test, we have 10 people each who are female and male, and I have their ages. So we are going to perform our Z test. Now, before getting into this, let's try to understand what exactly a Z test and what's going to be our null hypothesis and alternate hypothesis for this particular example. A Z-test is used to compare the mean of two given samples and infer whether they are from the same distribution or not. We do not implement Z-test when the sample size is less than 30. We know that here in this case the sample size is less than 30, so Z-test is logically not applicable here, but we will try to apply and see and interpret. If we applied Z-test, what would have been the scenario, whether we will accept the null hypothesis or reject the null hypothesis or something like that. Before getting into this problem, let us try to note down our null hypothesis. Before noting down the null hypothesis, I am repeating once again, this data is of 20 customers or 20 people, 10 females and 10 males, and I have their ages, different ages. So here my null hypothesis will be there is no significant difference between the mean age of males and females. And the alternate hypothesis will be the opposite of it. There is a significant difference between the mean age of males and females. In this particular example, I'm going to use the significance level as 0.05, which we already know that most of the statisticians use this significance level. So whatever p-value we will get from this Z-test, based on that we will be deciding whether to accept or reject the null hypothesis. We already know the conditions. If my p-value is greater than 0.05, which means we have to accept the null hypothesis, and if p-value is less than 0.05, then we have to reject the null hypothesis. I hope everybody is clear on this thing. Now what I need to do is, before getting into that, let me discuss about the formula of the Z-test. Z-test is basically your x1 bar minus x2 bar. X1 bar is your this mean age of female. X2 bar is the mean age of your males for the sample population. Mu1 is the mean of your population data for the female customers, and mu2 is the population mean of the male customers. Sigma 1 is our standard deviation for female, sigma 2 is the standard deviation of male, n1 is the number of count for the female customers, and n2 is for the male customers. Simple. So how to perform the Z test? I'm pretty much sure this option might not be visible in your Excel sheets. What you need to do right now is simply go to File and go to these options, and here you will be able to see add-ins, and here in my case this analysis tool pack is already activated. In your case you have to activate that pack. There are so many blogs and videos which you can take reference from and activate the pack. So once your pack is activated, you might have to restart your Excel. You just restart your Excel and get started with again. Now I will quickly jump into the Z test part. So I'm going to click on this data and then click on data analysis. You can see when I'm clicking on data analysis, I'm able to see a lot of options that is related to data analysis. In this case, I'm going to perform the Z test, to sample for means. Before getting into that, I would also need to calculate the variance of female and male ages. So here I will note down var1 and var2, and I'm going to calculate the variance of the female users, and same I will just drag it so that it will auto calculate for the male users. Now these are the two variances that we have. So 9.95 is the variance of female age, and for male age it is 14.32. So I'll click on data, go to data analysis. Now here I'm going to click on the Z test to sample for means. The moment I click, you can see automatically some of these values are auto populated because uh, I was kind of doing some practice just few minutes back. So you, in your case, everything should be null. So you should look like, your window should look like this. How to get started? Click on this and then it will ask for a range of the first column. So pass it. Similarly for this, the range of the second column. As you have already included the headers, click on labels. By default, it will be turned off. Click on labels. My hypothesized mean difference will be 0 because I'm assuming that the population difference is 0. That's my assumption, right? That there is no significant difference between the mean age of male and female. So my hypothesized mean difference will be 0. The variable 1 variance will be 9.95. The variable 2 variance will be 14.32. Alpha is my significance level, which is set as 0.05. Where do you want the output? Let's say I'll click on this and click on this. That means I need the output in this cell. The moment I click on OK, you can see my Z test output is ready. Now, how to interpret this table? It's very simple. The first is your mean value. So for female age, the mean value is 22. If you want to validate that, you can probably validate that in a different cell, and you can see the average of the female age is 28.2, and same, the average age of the male will be 25.9. The variance is already predefined. How many observations do we have? We have 10 observations. Hypothesized mean difference is 0. Now, I hope everybody knows about one tail test and two tail test, right? Now, in this case, you can basically consider any of this, either one tail or two tail, but in both the cases, your p value is greater than 0.05. And as p value is greater than 0.05, which means we have to accept the null hypothesis. So in this particular example, we are going to accept the null hypothesis and conclude that there is no significant difference between the mean age of male and females. And obviously the age of female is 28.2, age of male is 25.9. It looks little bit different from human point of view, but from this particular statistical test, we conclude that there is no significant difference between the mean age of males and females. Now, this is how you calculate your Z test using Excel. You can also perform this test using Python as well. So there are different strategies, different libraries that you will be using to calculate, which we might study in future. But as of now, that's all about this particular topic on Z test. In the next videos, we shall be talking about various other tests related to t test, correlation, chi-square, ANOVA, and so on. So see you in the next video. Hi, welcome to this module on statistics, and in this video we shall be talking about the chi-square test, or people call it as chi-square test. Now, chi-square test is basically used for categorical data. Now, as I already told you that this test only works for categorical data, which means the data which are in categories. For example, gender, male or female, or color, red, yellow, green, etc. In this particular example, I have two categorical features, one of them being gender, which has two valid values, and one of them being location, which has three valid values, which is Japan, India, and Korea. Now, you can see the formula of chi-square is basically summation of observed minus expected value to the power of 2 divided by expected. Now, what is observed and what is expected value? I'll try to explain. So before getting into this problem, we'll try to create our null hypothesis and alternate hypothesis, because ultimately we are going to use chi-square in order to check and test our hypothesis. I hope everybody knows about hypothesis, as we already covered what is hypothesis. Simply a hypothesis is a statement that might be true, which can be tested. In this particular example, let me write down my null hypothesis, which will be there is no association between gender and location. The alternate hypothesis will be there is an association between gender and location. All good. If p value is greater than 0.05, that means I will reject my null hypothesis. If the p value is less than 0.05, that means I will accept my null hypothesis. Now comes the first thing, is what is O, what is E? O is basically observed values and E is basically your expected values. In order to find the observed values, I'll take help of pivot table. So I will ask the table range to be this and location of my output to be somewhere here. Done. My gender, I will drag it to my rows, location in my columns, gender in the values, and that's my pivot table. So I'll kind of copy paste this pivot table to create my observed values. So I'll just delete all these labels. I'll just take these values, okay? And here I will note it down as observed values. So these are my observed values. My female customers staying in India are 6, females staying in Japan are 6, females staying in Korea are 0, males staying in India are 2, 2 and 4. This is my row total. I will write it down as my row total, and this will be my column total, and basically this value 20 is nothing but my grand total. Okay, simple. Now that's my observed values. Similarly, I will create another table for my expected values. I will empty all these records because I don't need all these things, right? Now, how to calculate the expected values? It's very simple. Expected values are nothing but row total multiplied with column total divided by grand total. Simple. That means the expected value for Indian female customers are the row total multiplied with the column total divided by the grand total, which is 4.8. Similarly, for Japan will be row total divided by this, multiplied with this divided by the grand total. Korea will be, the row total will be 12 multiplied with this divided by this, which will be 2.4. For male will be this multiplied with this divided by this is 3.2. And for male Japan will be this multiplied with this divided by this, which is similar to India. And for Korea will be this multiplied with this divided by this, which makes it 1.16. Everybody is clear with this table? I will simply copy this and paste it. I will delete all these values because I'm not going to take help of that. And this particular thing is nothing but my this operation O. I will write it down as O minus E to the power of 2 divided by E. Okay, that's the mathematical expression, same as this one. So what will be this? This will be observed minus expected, give it a bracket, to the power of 2 divided by expected, that is 0.3. I will drag it for these three values and drag it for these three. Cool. So you can see, I'll repeat once again, this is nothing but my observed 6 minus 4.8, which is 1.2, to the power of 2, which will be 1.44 divided by 4.8. So O minus E to the power of 2 divided by E. If you want to validate this one, let's say for this one, it will be this value minus this value to the power of 2, which is 1.2 to the power of 2 divided by 3.2. Okay. Now, what will be my summation of this operation? The sum of this operation, my sum of this operation is nothing but, I will write it down here. This will be sum of all these values, which is nothing but 7.5. So this basically becomes my x square value. X square value. This is nothing but my chi square value. What will be my df, which is my degree of freedom? My degree of freedom formula is very simple. Degree of freedom is nothing but my row total, like the valid values in row minus 1 multiplied with column minus 1, which basically means how many rows do we have here? Female and male. Minus 1 is 1. How many columns do we have? India, Japan and Korea. Minus 1 is 2. So it will be row minus 1 multiplied with column minus 1. Okay. So DF value will be 2. 1 multiplied with 2. Now this is where I will calculate my p-value. My p-value formula is, I will use the chi square dot dis dot rt, which basically means it returns the right-tailed probability of the chi-square distribution. I'll call it, I will pass my x square value, pass my degree of freedom, press enter, and my p-value is 0.02. I will try to create a table out of it. That becomes my p-value 0.02. And as p-value is less than 0.05, that means we are going to accept our null hypothesis, which means there is no association between gender and location. So my p-value is going to be 0.02, which is less than 0.05. So our null hypothesis is going to be accepted, which means there is no association between gender and location. That is an end to this particular session on chi-square. That's it. See you in the next videos for further topics. Bye. Hi, welcome to this module on statistics, and in this video we shall be focused on the last test, which is called as ANOVA. ANOVA simply stands for Analysis of Variance. It's a statistical test that is used to check if the means of two or more groups are significantly different from each other. It's a parametric test for hypothesis testing. Now, before getting into our hypothesis testing, talking about our null hypothesis or alternate hypothesis, I want to focus something on the parametric keyword. What do you mean by parametric and what do you mean by non-parametric? The key difference between parametric and non-parametric test is that the parametric test relies on statistical distributions in data, whereas non-parametric do not depend on any distribution. Parametric is a statistical test which assumes parameters and the distributions about the population are known. It uses a mean value to measure the central tendency, and these tests are common and therefore the process of performing research is simple. And talking about parametric tests, there are multiple tests which are parametric, including t-tests, z-tests and ANOVA. So ANOVA is a parametric test as well. Now, getting deep into this particular example. As I talked about, that ANOVA is nothing but a statistical technique that is used to check if the means of two or more groups are significantly different from each other. Now, let's talk about this particular example. As you can see, there are three types of groups. cholesterol lowering drug and cholesterol levels. So there are three groups which are given with different doses of drugs. Group A with 0 mg, Group B with 50 mg, and Group C with 100 mg, and these are the cholesterol level of multiple patients. Now, talking about this example, what should be our null hypothesis? The null hypothesis here has to be mean 1 equals to mean 2 equals to mean 3. In simple terms, there is no significant difference between mean values of each group. And my alternate hypothesis means aren't equal. That means there is a significant difference between mean values of each group. I hope everybody is clear with the null hypothesis and the alternate hypothesis. Now, there are certain things that we need to discuss here. One of them is sum of squares. Sum of squares, which is also called as SS, is nothing but it quantifies the variability within the group. Let me write down everything, and once we run the ANOVA test, I will have a better explanation about all these things. Degrees of freedom, which is also denoted as DF in statistics. Now, DF between the groups, and there is another concept called as DF within the groups. Now, DF between the groups, the formula is simple, number of groups minus 1. So what will be the DF between the groups in this particular example? It will be 3 groups minus 1, which is 2. And DF within the groups is going to be number of observations minus number of groups, which in this case will be 27 minus 3, which is 24. My mean squared value or MS, it is the average variation either between groups or within groups. The formula is MS equals to SS by DF. So done. Then comes your F statistics. F statistics, it is the test statistics in one-way ANOVA. F is basically MS between the groups divided by MS within the groups. MS is basically our mean squared value. Now, talking about our final statement, if p value is greater than the significance value or significance level, in that case, we accept the null hypothesis. Else not. And we all know what is our significance value is basically 0.05. Now, let's try to call our data analysis operation and call the ANOVA. I'll click on data analysis and I will call on the ANOVA single factor. And here it is asking for input range. I will click on input range and then I will select everything. And as I have selected the labels as well, I will be checking the labels. My alpha value or my significance value is 0.05 and output range, I want it in this particular location. Click on OK, and this is how your ANOVA single factor summary and ANOVA table looks like. It is divided into two things. The first being your summary statistics, and the second being your ANOVA values. Now, summary statistics is quite simple. For each group, it has calculated the count and the sum. If you want to validate for group A, the sum is 2380 and the sum here is 2380. For group B, the sum is 2170, the sum is 2170. Average is 241, average is 241. If you want to validate the variance, let's blindly validate the variance for my third column And here you go, the variance is 411, which is 411. Everything looks good. Now comes the main table, which is ANOVA table. So my between the groups SS calculation is 14,007 and within the groups is 14,000. Now DF is 2 for between the groups, because between the groups formula is number of groups minus 1. Here we have 3 groups, so 3 minus 1 is 2. So that's why we have 2 here. Within the groups, it is number of observations minus number of groups. So 27 minus 3, which is 24. MS value is this divided by this. SS divided by DF. You can see this formula. The F value is 12, P value is 0.000243 and F critical value is 3.4. There are two ways to check your ANOVA scores, but as we are considering the P value, talking about the p-value, the p-value is way less than 0.05. So in this case, as my p-value is less than 0.05, we basically reject the null hypothesis. If the p-value is greater than 0.05, then we accept the null hypothesis. As it is less than 0.05, we reject the null hypothesis. So we conclude that the means are not equal. So we are kind of accepting the alternate hypothesis. So that's all about this particular video on ANOVA. I hope you had a good amount of understanding on ANOVA, and that is how you check your ANOVA score in Excel. That's all about this particular video. See you in the next video. Bye bye. Hi, welcome to this module on statistics, and in this video we shall be talking about the correlation test. Now, we all know what exactly is correlation. Correlation and covariance basically helps us to tell how the linear relationship between two variables looks like. Covariance somehow ranges from minus infinity to infinity, and magnitude has no meaning to it. But if you see a positive covariance, you can probably understand that there is a positive relationship between the two variables. That means if variable 1 increases, variable 2 increases. And if you see a negative covariance, you can probably identify that when variable 1 increases, variable 2 decreases. But in the case of correlation, we all know that the value ranges from -1 to 1, and magnitude is very important, which means if you see a number very close to 1, let's say between variable 2, let's say there are 4 variables, variable 1, variable 2, variable 3 and variable 4. If your correlation between variable 1 and variable 2 is 0.9 and the correlation between variable 3 and variable 4 is 0.8 or 0.6, which clearly means that this is a stronger relationship as compared to this. And other logics remains the same. If it is a positive number, that means it's a positive correlation. If it's a negative number, then it's a negative correlation. And if it's a number very near to 0, that means there is no correlation. Now on the screen you can see two examples. One of them is some of the data points for a particular from a particular set of customers. We have height and weights, and another example is again for certain amount of people we have the age and salary. Now our task is to create or find correlation between height and weight and age and salary separately. These two are two different examples. Now again, to accomplish this operation in Excel, we need to again take help of data and data analysis. But before going into that, I just wanted to show you how the scatter plot looks like. The way you need to create a scatter plot is very simple. Just select your data, go to insert, go to recommended charts and just click on this scatter plot. Now this is a scatter plot which is your weight versus height. You can see the first data point is 140, 61, which is this one. this is basically 156 and 65, which is this point, and this is how the plots has been created. Similarly, what I need to do is I will again do the same thing for age and salary. I will select the data, go to insert, go to recommended charts and click on the scatter plot. And this is how my scatter plot looks like for age versus salary, right? Now in this particular example, you can see almost there is a positive correlation. Just looking at the data, I can quite say that there is a good amount of positive correlation, which means when your weight increases, your height increases, and vice versa. Even in the case of age and salary, you can see it's an increasing trend for sure, right? So how do we calculate the correlation value? So I'll go to data, I'll go to data analysis, and here I will click on correlation. And here it is asking for input range. What is my input range? I will just select this. Done. Labels in my first row because I have the headers. I need the output in this cell, and then I'll click on OK. And this is how the correlation looks like. So the correlation value between height and weight is basically 0.94. Similarly, I will also do the same thing for age and salary. Click on this. Instead of this, I will click on this. Done. Labels in the first row. Instead of this, I will click on this and click OK. And you can see that age and salary are also having positive correlation. So that is basically giving you an idea that both of them, in fact height and weight, are also positively correlated with each one of them, and age and salary are also positively correlated, and the score is even higher than this, which means age and salary are more, the bond between age and salary is more, the positive correlation is more as compared to height versus weight, right? That's all about this particular topic on correlation. On top of that, in case you don't want to go through this data and data analysis, there is also an inbuilt functionality that you can use, which is basically just click on equals to correlation. So CORREL is the function. Select the array 1 and then comma, select the array 2, and then you can see the correlation value is 0.94. Same for age and salary. I will do equals to correlation. The function name is CORREL, and then I will pass my first array, and then I will pass my second array, and then the value is 0.96. So this is how we analyze two numerical features. This is how we analyze two numerical features, and this is how we calculate the correlation. And based on the correlation test, we basically conclude whether there is a positive correlation between two variables or not. That's all about this particular topic on correlation test. In the next video, we shall be talking about various other tests, which is t-test, chi-square, ANOVA, etc., etc. See you in the next video. Bye bye.